Good morning, everybody. Welcome to GRIPS. I'm David Greenfield. I'm your chair for the first session on the materials panel, or the materials theatre. You're very welcome, and good to see so many of you here today. So, I have a few announcements. Firstly, housekeeping. There is no fire alarm scheduled for today, so if the fire alarm sounds, please leave the building via the nearest fire exit, which is there, there, or there. This is where I get into aeroplane mode. And as directed by the designated fire marshals, do not use the lift. The assembly point is the car park at the rear of the building. So that's quite simple. Today we're going to be talking all sorts of different materials. We've got a fascinating session to begin with, followed by a break, and we've got a brilliant panel discussion. Firstly, though, I'd like to extend our gratitude and thanks to the sponsors, the Grantham Centre for Sustainable Future, Plastics Europe, and the worshipful company of Horners, who have made a kind donation to the event in memory of David Williams. Without them, this event would not be possible. So thank you very much to the worshipful company of Horners. Okay, so we're going to be talking GRIPS today. Our first panel is, hopefully if I can click that correctly, Additives, a New Frontier. We have some brilliant panellists. Sarah Lightowler from Cargill, Onnicha Rattanopas from Interface Polymers, James Donaldson from Sortology, and Professor George Fern from Brunel University. If you're not here for this session, go now. If you are, stay. Good. Additives, a New Frontier. It's quite a curious title, that. We all know that in plastics there are all sorts of things that the public haven't got a clue that are in them. And we know that at different stages of the life cycle, they cause problems or opportunities. So today we're going to be having some really fascinating presentations into some of the challenges and opportunities that arise from additives, why they're there, how we keep them there, how we capture them, or how they become a problem. As I said, we've got 4 brilliant speakers. We're going to have presentations, and then we're going to have time for a panel discussion. So if you do have questions, please keep them till the panel discussion. We won't do any Q&A as we go along. And then as part of the panel discussion, I want some interaction from the audience as well, as long as we have time. So that's a little note to the presenters to be nice and tight on time. We have got until 10:30, so we've got a bit of time. So, just a tiny little bit about myself, because I always forget to do that, and everyone goes, what on earth do you do? So I'm co-founder of a venture studio called etsaW, which is Waste in Reverse. We invest in early stage startups that are looking to capture materials from the existing urban mine, and then create new materials, or indeed create new materials from some secondary raw materials. The venture studio is very different to a venture capitalist. We have small amounts of money, but huge amounts of expertise. It's quite nice. And our role is essentially to take early stage founders through the scaling process. So when we get involved in a company that's external, we'll actually put in our expertise, and my co-founders range from being entrepreneurs to circular designers. But we also have the ability to create our own company. So we've created one that is extracting collagen from fish waste, and we're just creating an AI tool that can do deep dives into the material futures of individual polymers. I have a few other roles as well. If you're interested, go into my LinkedIn. So today's not about me. It's about our panellists. So I'm going to introduce Sarah Lightowler from Cargill to come up and give our first presentation. Sarah, thank you very much for coming today. And would you like the mic, or would you like the lectern stand? There we go. Choice for presenters. There we go. Thank you, Sarah.
Thank you very much. I feel this looks a bit too low down. So hi everyone, I'm Sarah from Cargill. I'm our Business Development Manager for Circular Plastics. And today I want to talk about our bio-based additives, but really looking at how they work in mechanical recycling and how they can help protect polyolefins from further degradation during those recycling loops. I'll be quick on time and do some very quick introductions to Cargill, because it's never people's favourite part to learn about other companies. But Cargill, very large company, normally known for agriculture and food. So you can see our purpose, nourishing the world in a safe and responsible way. Cargill made the decision to buy my part of Croda 2 years ago. So some people still know us as Croda Polymer Additives. We are the same people, the same products. We are just now under the Cargill brand. Cargill, very large company, 160,000 across many, many countries of the world, and serving all types of market. So it does actually really help us in the polymer industry. All our products are 100% bio-based. We now have a very transparent supply chain because we work directly with the farmers that grow the crops for us. We can work with them on their regenerative agriculture. We can have that full look at full scope 3s and be able to work out what we want to do in the future. So, big positive. So the type of additives I want to discuss today, this is our full range. So we're mainly known for friction control, slip additives, so into all sorts of different polymers. Everything we do is, I say, small additives added at 0.5% or lower that are added in to give an effect at the surface. I won't be mentioning anything to do with static control, but we have got some really cool additives. So if you have different questions, do grab me at another point of the day. But today I'll be focusing on our InquaSlip range, which was developed for caps and closures and food packaging. So very stable slip additives, great torque release, and has all the correct food contact approvals, and more stability. So say this is what they were developed for, to optimize the benefits in food packaging and to allow that easier processing and handling of all plastic materials. But these hit the market maybe 20, 30 years ago now. We've had some new ones since then that are with different chemistries. But when they were developed, we never thought about the end of life and what happens to that material and how do our additives, even if they're only added in at 0.5%, that could be the blocking point for recyclability or for biodegradation. So that's where we started back in 2018. We thought, everyone's starting to talk about the circular economy. How does that affect us? Is that a good opportunity for us? And this always really shocked me, all these conferences I went to, and you look at year on year, how globally the circularity is actually declining, which is really depressing when this is 100% of your job and you're working on trying to improve everything. And yes, you can justify, look through the figures of the pandemic and population growth, but I hope it's something that really drives people to want to work in this area and to help improve the world and do the right thing. So this is what we aim for 2040. These are figures from the Ellen MacArthur Foundation, not Cargill, to be clear, but it's the driving force to think that by 2040, if we all work together across industry, that we can actually reduce the amount of plastic entering the oceans, we can reduce greenhouse gas emissions. There's a lot of money to be made, which is also the corporate drive to do this at the same time. And for those of us that work in this, it's nice to see that it is an area that is growing, that we will be employing more people to help and work within this area. So this is the goal I set Cargill, or my part of the business, in 2018, to create circular and resource-efficient solutions. And as I say, we want to work with industry. We've never thought we could do this by ourselves. So we work through reduce, reuse, recycle, and redesign. And we've said additives on the market have always helped with reduction of virgin plastic use, so better mold release, fewer rejects, thinner moldings, thinner films. That's something we've always done, but is now of more interest to people. We've got those stable slip additives that are great for reuse applications. So a lot of scratch resistance, better aesthetics, plastic's not yellowing as quickly. But where my team are really focusing is on those new additives. What do they do in mechanical recycling currently? and also how can we help in that redesign section. So really looking at what's needed for monomaterial design, what's missing, how can additives have a part to play in that part. So that's where I'll be focusing today. I'll focus just on polyethylene for time, but if you want to discuss other polymers, grab me afterwards. We did some work at Aimplas, which is a testing house down in Spain, in Valencia. Great people to work with, and they've got a small recycling plant, I guess, pilot plant that they can do some testing at. So what we did, we wanted to test our slip additive. So we tested Incraslip C at 0.5%. We added it to virgin polyethylene, and we did a full loop of mechanical recycling, and we called this our post-industrial waste or in-house scrap. And we then split this into two different sections. We carried on doing in-house scrap to see what effect the additive would have over multiple loops, but then we wanted to replicate post-consumer as well. We couldn't start from a true PCR at this point because we wanted to know the actual effect of our additive and not knowing other contaminants that might have been in the PCR, but we followed those washing and drying steps. So followed the Reciclass protocols for food contact applications, so that's 90 degrees, very harsh surfactants, caustic soda, so really pushing the additive to its limits. And we did this 3 times for 3 full loops with no further addition of the additive. It was just added at that very beginning point. And after each loop, we did full characterization of mechanical, optical, and rheology. I won't go through everything today, but what we wanted to see is, firstly, does the additive survive? So here you can see on the left that in post-industrial, when you don't have those washing steps, the additive survives 100%. As soon as you add that washing step at cycle 2, you lose half of the additive. But more excitingly for us, by cycle 3, it actually remained at that level. So the amount that still is in that bulk is remaining and not migrating back out of the plastic. And at 0.25%, you'd still get all the benefits you need of a slip additive. That would still be enough to give you great torque release and good performance. For today, hopefully don't have a weird animation, but I will keep flicking back. This is our main highlights. So the main one we talk about is the flow, which I'll come on to very quickly. But otherwise, we talk about the whiteness. I'll flick back once more so you can see the pictures. But there'll be the virgin plastic that you see is very white. As it gets degraded, it starts to get yellow. And hopefully the third picture, if I go now, you'll see keeps that whiteness of the recyclate. So for us, that is proof that we are protecting the polymer as it gets recycled. So there's less degradation. We never promise a white polymer because it obviously very much depends what else you have in your formulation. But we think it's a clear example that we're not degrading the polymer as much. But a better way to prove that we're not degrading it was to look at the flow. So we started looking at MFR, but then we do also realize that MFR is only 1 point. So I will go on to a full viscosity curve as well. But here, as polyethylene degrades and is recycled, it cross-links, you get these longer chains, it's harder to flow, and therefore you can see that the viscosity starts to drop down on the control that's on the left. As soon as you add the Incraslip C, so on the right-hand side, you can see we maintain the flow much closer to that virgin level. And by the third cycle, it's actually twice as high as if you don't have the additive. If we go to a full viscosity curve, so it's very busy to see all of them, so I've just zoomed in. On the right-hand side, you've got the red lines, which are the control samples. So you've got the solid line right in the middle, which is just the virgin polymer without the additive at cycle 0. And then the dotted red line at the top, that is the control sample after 3 loops of mechanical recycling. So you can see that the viscosity is increased quite dramatically there. Whereas when you look at the green lines, that's with the Incraslip C. And whether it's the solid line or the dotted line, you can see that it's absolutely remained on that same level of the virgin. And this is, we see a lot more in the extrusion range back here. So hopefully you agree, clear sign that we are protecting that polymer from the degradation. I will skip through polypropylene and go to my summary slide, because that's my 1-minute warning. But this is what we wanted to discuss in the panel study, and happy to pick up any discussions afterwards as well. But we know that our bio-based amides are in there as a slip additive, but you see that as they get recycled, they're reducing that shear stress. As they go through the machinery, you're having lower shear heat induced processing. It's getting less degraded, and therefore we think you could therefore have that recycle it and use it for additional loops, and it would have a higher quality of recyclate. So quite excited about the data and very happy to discuss afterwards. Thank you very much.
Thank you, Sarah. That was great. Make sure you've got some questions for Sarah. I've already got a couple. We're going to go straight on to our second presenter, who is Onnicha, and I'm going to really difficult to pronounce, Rattanopas. Oh, good, that's good. Who's going to talk to us about interface, and we look forward to hearing from you.
Thank you. Okay, I think I'm going to be sitting and use the pointer in the program so that I can point like 2 screens. No, I mean in the program so that I can point like in the 2 screens at a time, so people on that side could see where I'm pointing as well. Right. Okay. So yeah. Hi everyone, I'm Onnicha Rattanopas. I'm a polymer applications leader at Interface Polymer. Interface Polymer is a spun out from Warwick, University of Warwick. It was our founder's PhD project. He discovered this diblocker polymer molecule that we always, I always describe it as a platform, and I tell you a bit later why. So yeah, today I'm going to be presenting about using polyolefin compatibilization technologies to improve the recycling of multi-material packaging. Okay. Right. So I think we all know that multi-layer or multi-material packaging composed of like variety of material, and each material has different functions. For example, like nylon, like polyamide, or EVOH, it has like good barrier property, and that other materials like PET, that's good for printability, and also polyethylene or polypropylene as well. And once you try to recycle these multi-material packaging, you will find all these problems, like imbalanced mechanical properties, poor printability, low quality gels, poor optical properties. So I say due to this incompatibility issues, the multi-layer or multi-material packaging is not recyclable. So yeah, try to imagine if like people in the industry is in one chat group and what they say. So this is like a family. I would say, let's say they are representative of like consumer. I mean, mostly they don't know how bad would it be. We just try to recycle all this packaging. And this is, I say he's a representative of recycler, and once you try to just recycle, those multi-material packaging, this is what you see. So yeah, this is just an example. It's 80% polyethylene, 20% nylon 6 blend together. You can see all the flow marks. And if you try to tell it, you see the split in like flow direction, and you can see lots of gels and rough surface. So yeah. yeah, that's bad. So yeah, and this guy, he's a representative of converter. Most of them try to use like compatibilisers in the market, and of course it works to some extent. The problem is that they have to use very high amount of compatibilisers, and I say it's not economically viable. So yeah, this is well, you've seen this one from the previous slide, and yeah, this one is the film with 2% of the grafted product. You can see some improvements, of course. There are fewer flow marks, but still weak in like machine direction, and there's some gels and with like smoother surface. Right, that helps. Yeah, but the question is, can we do better? And that's supposed to look like me, but that's yeah, okay, let me show you how we can do better. Let's talk about our die block copolymer technology. Unlike other compatibilisers in the market, polyolefin die block copolymer works as a polymer surfactant in polyolefin and polar polymer blend. Let me tell you why and how. So our die block copolymer composed of 3 segments, I would say, like the polyolefin segment. It can either be polyethylene or polypropylene, like we can choose. We can change the block length and everything. And another block is polar polymer. Again, we can change the monomer type to make sure that we can design it to serve like different applications, not just as a compatibilizer. And these 2 segments are linked by the bridge molecule, which I'm not going to tell you what it is. So imagine you try to blend, let's say, 80% polyethylene, 20% nylon together, and do the SEM. You can see the big domain size of nylon floating in the polyethylene domain, just like that. But once you add, let's say, 2% of polyolefin in it, what polyolefin does, it will, once you kind of blend everything together, the polar block of polyolefin will like chemically entangle with the polyamide while turning this polyolefin parts out to entangle with the polyolefin domain, matrix. Sorry. As a result, you get much smaller and more uniform nylon domain. So yeah, you've seen these 2 images from previous slides. And what happened when you use polyolefin? So you can see like big improvement from no compatibilizer or from the grafted product. You can see that there's no material defects, and if you try to tear it, you get like superior and more balanced test strength and smoother surface. And actually, this 20% nylon is not the limitation of our technology. You can even add the like 30% nylon, or this compatibilizer also works with, let's say, 70% nylon and 30% polyethylene, basically. So yeah, and these are the ACM images of the formulations that I showed in the previous slide. So the first one is the blend without compatibilizer. You can see all the big particle size of nylon in polyethylene domain, and with the grafted product, you can see that the domain size of the nylon are smaller, but still not as uniform or as small as comparing to the blend with our polyolefin. And you can see that in the blend with polyolefin, the domain, the nylon domain is dispersed and encapsulated by the polyethylene matrix. So yeah, just show you a little bit of the effect of the addition rates on the domain size, the nylon domain size, and the clarity. And you can see that once you keep adding or increasing the addition rate of polyolefin, you can see that the domain size keeps getting smaller, and you can't even see the plateau of this decreasing domain size yet, even with 5% polyolefin. And as a result, we get the higher clarity and lower haze. And so yeah, for the mechanical property, in this case, I'm just showing this test strength. Polyolefin gives the highest, oh, I've got 1 minute, sorry, I have to be quick. Highest test strength at 2% polyolefin. So yeah, we've done the Innovate UK project with Flexsea. We call it recycle ready film. So basically, first step, we add polyolefin in one of the layer of that 7-layer film, and then they recycle it and put 30% recyclate back into one of the layers. And this is what we got. The one without polyolefin, you can see that, well, you can see the rough surface. Meanwhile, with 4% polyolefin, you can see the smoother surface. Right, okay, let's challenge polyolefin a little bit more. So previously, I just showed the blend between polyethylene and nylon, which is pretty common. So we've done some work on polyethylene and EVOH as well, and also polyethylene and PET, where PET is minority. And well, we have the polypropylene version of Compatibilisers as well, and we've done some work with nylon, and also we've done some work on the PE blend, where the PET is a majority. And yes, we've done some work on the 3 components blend as well: polypropylene, EVOH, and tie layer. Yeah, you can see all the improvements, especially the optical properties. And we've done some work with the mix, very nasty mix recyclates. And this one, we've done some work with the Indian recycler. So you can see, well, according to the SEM image, you can see that after adding 5% of dye block into it, the domain size of the dispersed phase is smaller and better bound to the matrix. Yeah. So yeah, I say with our compatibilizer, you can see, solve all the issues caused by incompatibility of materials. Right. I know I was too quick, but if you like to know more or you'd like to request a presentation, just let me know. And yeah, I can send you the presentation. Thank you.
Thank you, Onnicha. That's great. Really interesting presentation. Lots of microscopic images. We like that. Right. Now we're going to go on to our third speaker, James Donaldson, who has been around this sector for a little while, I think it'd be fair to say. James, we look forward to your presentation.
Hiya, I'm James Donaldson. Very briefly, I've been around. We do deinking technology. I designed the Berry PP plant. We do splitting, do all sorts of things. I'm here to talk about inks, though, today. So inks are what we add for decorative and functional purposes to packaging. Now, the thing about inks is a lot of them are food safe in their application. So when you print them between layers, they're fine. When we come to recycling, we stick them through an extruder, which to an ink is a low temperature pyrolysis, in effect. And the inks break down in all sorts of fashions. If you've been to a recycling plant and smelt the vacuum ports, which I have, they're horrible. So the thing about inks then is they decompose only partially, so it's not a binary. A bit of them breaks down through each heat cycle. In film, this causes gels and bubbles. The breakdown species that I'll show you can be very toxic. You get a poor colour, and in our marketing world, colour is still very important, so people want natural or white. They don't want black in their products. And also, you can smell it. And I know not many of you will smell bin bags, but I smell bin bags in the supermarkets. You can smell the recycled content. You can smell how well they're done. The first issue is the biggest. So this slide has a lot on it. To the right is the plant we built with Coveris, so I think one of them is here, using our chemistry and ceramics technology, and this is what it does. It takes film and de-inks it. What I'm going to talk about, though, is inks breaking down. And I'm going to talk about the yellow diacrylide, which is a yellow pigment, and people should say, oh, why are we still using it? Because it replaced cadmium yellow. So cadmium's worse than this, okay? When you heat diacrylide yellow pigments, and this is at 1%, the bit in red, it breaks down, and those levels are parts per million in the whole plastic. And it breaks down to dichlorobenzidine, which is the equivalent toxicity of PCBs. And to emphasize this, I have the comment, that is off the comment in red is off a current data sheet. And it says, above 200, the pigment may decompose to form measurable levels of DCB, which is a suspected human carcinogen. So that's on the data sheet. That's on the data sheet today. So this is why decomposition of pigments is of interest. Now, during lockdown, I got bored. So I wrote a full EFSA application for food grade de-inking. I got very bored. We discussed it 3 years with EFSA, and they actually rejected it the day before legislation stays. But the reason they rejected it is quite interesting. Basically, what we said is slide 1. Can we use there? Slide 1 shows the printed system. So what you have is you have ink layers, and then you have the species that have migrated into the plastic naturally and additives. When we de-ink, nothing in recycling is 100%. Okay? There's always something left behind. Whenever you clean something, you leave a residue. So nothing's 100%. So we leave a bit of ink. And I'm sorry about my artwork. Now, I did a lot of work, and I worked out that the issue with that equilibrium decomposition is that only, let's say, 99% of the ink decomposes on that first step. So when you recycle it, make it back into a pellet, and your customer puts it through their extrusion line, even if it's food grade beforehand, if you've left enough ink, it'll break down again, because it's an equilibrium decomposition, and form species in direct food contact. So my argument, which is long-winded and thing, is at 165 parts per million, you can, of ink remaining, even if it breaks down in the worst fashion, and you put it directly into a food product, it'll migrate at levels, and I use, because we had an argument years ago, at the baby level, at the child level, rather than the higher adult level. And that was the basis of my argument, and we added lots of other things. The reason EFSA didn't like it, and there were a few other reasons, is that basically we couldn't give an ink data sheet. And what they said is that because you cannot do a full risk assessment on the ink, you cannot work out what to look for in the finished product, therefore you can't check it properly. Now, that has some interesting consequences for the industry, because The ingredients in inks are a huge range of species. Every ink company is confidential, and the breakdown products of these complex long species is nearly infinite. It's the same argument, interestingly, we had with them. I did the application for Biffa's food-grade HDPE, and the argument is what is in the milk bottle, and then prove you've removed it. And what we go is we've got 10 years data of clean polymer. This argument is actually becomes quite interesting for recycling. What I neglected to say is this application was for known batches of post-industrial material, and I put it through a gatekeeper's test. So you knew exactly what was in it, you could test it at the end, and EFSA said, still, that wasn't good enough. So the implications is that you can't recycle inked product of any species. The safety case links to all de-inking systems, because if EFSA are focusing on the front end, what's in the ink, and not the quality of the back end, then everybody has the same problem. And there's also people who are looking at food-grade things. The one thing I will say, on all the tests I've done, and I've done a lot of tests, food safety itself is never an issue. I've put some horrendous things through recycling processes to test them. For food grade, I put all the rejected bottles, they pass. The issue is actually getting through EFSA's paperwork. So what do we do? I think the ink manufacturers are going to have to have a bit of a think. We need to look at gatekeeper tests, which is what I use to try and get around it. And also, we're going to need to work with EFSA to make them look at the end product rather than the starting issue. But summary, de-inking is important for lots of products. To get the same product our previous speaker was talking about, people want good quality products. This helps get it, and our chemistry is great. Okay.
Thank you very much. Thank you, James. Really stimulating talk, which I'm sure we can discuss in the panel. And finally, our speaker for this morning is Professor George Fern from Brunel, who's got a little bag of something which I'm a little bit concerned about now. Here you are, George.
What do I do? It's on. It's just on, is it? Fantastic. Very good. Thanks for coming to see my talk today. That's very kind of you. Do you hear me okay? Excellent. Brilliant. So just a little bit about me before we crack on with what we're doing. I think we're not quite as advanced as the last talk yet, looking at all our decomposition products, but hopefully that will come in the future. So I'm at Brunel University. We do lots of extrusion processing of materials. I found my way into being director of our experimental techniques centre. Some of you may have seen the Radio 4 programme in the summer about talc on BBC Sounds now, which might be interesting if you use talcum powder, for instance. I'm not going to talk about that today. My background is in lighting materials, so I'm interested in colour. So colour is really important to me. We're part funded by Innovate, so a couple of projects. So this is the sort of things we end up doing. Just throw anything through an extruder, we do, because we're not bound by manufacturing like you guys mostly. So if we can extrude it, we'll stick it down there and see what happens. So we pelletize, we make sheets, we blow film, and then we injection mold something to look at the mechanical properties generally. So they're the sort of things we're into. And we do some weathering, solar weathering testing, that sort of thing. Of course, mechanical. So they're all the sorts of things that are critically important to what we're doing. Hopefully, what you're interested in. So colour, so we heard about colour very briefly, but I just wanted to say a bit more about the true importance, really. At the end of the day, I've put in research grant proposals, and they said, great, very laudable, but where's the business in it? Right, so that's just no use whatsoever. So I learnt my lesson very quickly. So working with Brian Walmsley, great commercial guy. He was using some online market research people, looking at how are we going to develop a new product. This is recycled polypropylene products, right? Most of you will say, well, there's no recycled food grade PP around, so yeah, we don't have a chopping board. This was just a kind of check to see what people like the look of. The bottom line was, they said, we really love this style of chopping board, recycled product. But, you know, the key question is, would you purchase it? And it was unanimous no, right? So we love it, but we wouldn't buy it. So actually, you can see in John Lewis Next, places now, these sorts of products that are all just a single white, grey. There's now a green just come out. So people want colour, but you know, I'm thinking more about the future, the sustainability, what comes next. So what can we do? Working very much with the master batchers that I know, it's quite useful to find out what they add. You know, like we're hearing about toxic chemicals, all these additives, they just chuck lots of stuff in, right? So I can do certain things. But, so we put in all sorts of fibrous plant materials, you name it, we'll stick it in there. But we've been looking at some other things recently. So I just wanted to highlight a few things that other people have done. You know, this bit is from a Spanish group, but very much what we're doing as well, looking at plant-based pigments. So we have a project looking at textiles pigments at the moment. And I said, well, you know, this is an extrusion center. We want to put these into polymers and see what happens. You know, will they actually survive in the first place? Will they just be bleached anyway in the temperature? So, I mean, there's evidence out there where you take these carotenoids, anthracite, chlorophylls into your greens. Can you put them in the extruder? Can you get some nice colors out? What happens initially to the mechanicals, to the pigment itself? What can you do with it usefully? Right, so you can get a range of colors. Some people ferment their pigments. Right, so they do fermentation, give off CO2. This is not quite what we want to do. So we've got a couple of our partners here today. We've got Broadway Colours with Zoe here. She'll be by the poster we have outside. And DJ, put your hand up. So DJ is actually the founder of Broadway Colour, Post Carbon Lab, sorry. And also we have some EPSRC funding that's able to do a PhD. So she's just started a PhD at Brunel. So DJ's company is actually making algae-based pigments. But there's evidence from what we see in the literature. This was at 2 to 6 weight%. Colour fastness isn't amazing, so you're not going to be able to do much outside with these materials, but can you think of things to do that aren't exposed to full sunlight? Right. So that's what we're looking for, really. Mechanical properties, these were at 2 to 6 weight%. The plaques I've got, you'll need to see them by the poster, probably. I think ours were at 1%. But the mechanical properties of these ones at 2% were not affecting the product at all. So the sort of things we're looking at are these sorts of pigments. They're grown in tanks, absorbing CO2. The current Innovate project we have, little design project we're going, is some LCA just about to take place. But we think that the pigments are absorbing CO2, other things, not CO2 negative at least. Hopefully that will fall out with more work going on. So at the moment we've looked at a red sort of pigment and a green initially. Now we have done this in a bioplastic, but I wasn't able to talk about it today, sort of something you might pull out of the sea. But this is in polyethylene, we've done it in polypropylene. The plaques are all polyethylene actually that we've got here. And you know, initially we were quite encouraged that we see colour still. You know, we didn't know that would really be happening. We tried this on our little mini extruder where people come along with sort of high value products, 10 grams of material. We didn't get fantastic distribution in that. So we have other bigger, how long have I got? 2 minutes, okay. So we have bigger extruders, and these were processed then at Broadway Colours, and we're getting much nicer distribution. We'll see on the plaques. We've got these plaques with us, so you can have a look. So we have the plaques. You can see they're not, I don't know if you can see, they're not ideally, and they're a bit speckly still, but changing the process conditions, we're starting to improve the distribution. In fact, these ones have some whitening agent in as well. They're all polyethylene. They're quite nice colours outside, but sadly, you know, you can't see outside. But of course, to see colour properly, you need to sit under sunlight. Under the weathering station, this was at 23 hours. That other paper I said was like 50 hours. So they're not going to be great for exterior use, but shorter term, because having got 23 hours in a weathering station is quite harsh if you're thinking about the 21st of June in Miami, right? So it's probably the worst of all the situations. So really we're looking at what can we do with this next? Would it be better to put it in a bioplastic, for instance, something that's compostable? So we take it out of a plant, compost it. Who knows what we'd do if we actually put it through a hot processor sorting plant, what other products will get made. Yeah, it'll be interesting to find out. Environmental science have just joined us at Brunel, so we'll be able to do more of that work in-house, which is great. So the colour, I'm not going to talk about this now, but this is the reborn colour stuff. You can see we've got these grey materials, as I said, and greens come out. I'd love to persuade Brian to let us put some of these pigments in to see how they perform. Obviously, it's a business case, isn't it? What's good? Would it be better for a short-lived application? So yeah, they're my partners. The funders, Innovate, thanks, EPSRC2, and Post-Carbon Lab, Broadway Colours, obviously Reborn, and BIFA, actually, the post-industrial PP waste that we get from them, which is great. Of course, you have to find the right recycled material to put into your product. So not all recycled polymers are the same, I would say. Yeah, that's me.
I've now got my jacket hooked up to my... right, if all the panellists could come to the seats at the front. If you're all happy, we're going to go 5 minutes over 10:30, just so we can have 10 minutes discussion, as we started 10 minutes late. So, okay. Thank you very much for some really interesting presentations. Come down the front. Firstly, has anybody in the room got any specific questions you want to ask any of the panellists? Hands up. Okay. I just realised I'm now doing the mic passing as well. If you could just give your name briefly, where you come from, and a very brief question, so we can get lots of discussion, and that'd be great.
Good morning. I have a question for Sarah. It's Mike Boswell from Plastibition in the UK. I'm very interested in the recycling space, particularly in plastic films. And I like the technology. I understand what's going on from a polymeric viewpoint in terms of how your additives are helping to reduce shear degradation in recycling. But my question actually is, sometimes you don't want additives in recycled products. You don't actually want slip. Sometimes you also don't want cling type additives as well. So how do you deal with that?
Keep that there. It's the problem with being the first chair. You get all of the things we you forgot about that. All right, you can have that.
Thank you. Yeah, great question, and one that we hear quite a lot of additive build-up at recyclers. Not something we currently have an additive for, to kind of just, whether it's de-inking, whether it's just de-addivating everything, but it is something on our list, is all I'll say.
Oh, another question over there. A couple of questions coming up. Before we come to the panelists, I'm just going to ask everybody. Just a generic question, actually. Really interesting presentations from different perspectives. I'm coming from this from the end-of-life, next-life processing point of view. How challenging is it for the post-recycling or the recycling sector to be able to deal with some of the additives we're talking about? And for example, the slip additives, how are they going to keep going? Where do they go when they disperse in the system? And this whole life cycle thinking, how much of a challenge is that for us as a sector? Sarah, as you got the mic.
Guess I'll start.
Yeah.
So I think this is why we try and look in two halves. So we look at the post-industrial. If you're doing recycling your own scrap or you have a closed loop system, it's great because you know exactly what's in there. You know you won't have to add as much additives the next time. You can easily just measure the MFR, work out what you need the next time. So that, I think it's great. You're cutting costs, you're keeping material in the cycle. It's truly circular as long as you have that high quality. True PCR, much, much more difficult. And I think that's where we say we still want to work across industry to really help with some of those issues. So like our next range of additives that we're working on are very much focused on those areas, especially in flexibles and how you can meet more the plastic packaging taxes, include higher rates of PCR, but there's a lot of challenges.
Yeah, thanks a lot. So I guess my perspective on this is looking at what we do with the industry to make them, or to support them to develop a product. So like with the Reborn project there, we had BIFA material. That material worked brilliantly for us. That was the first material they were on board as a project partner. But of course, it's a research project. Innovate don't expect us to do stuff instantly. It will just work. And it was kind of unexpected that it worked so well for us. Then we went on to look at a lot of other materials, a lot of other recycled PPs. Actually, we had a lot of problems to get other materials to work. There were slightly different grades, but we thought they had the right outflow, but it wasn't very easy at all. You know, we'd done a lot of product testing and things were breaking, not ideal at all. So I think the additives are a challenge to know what we do next with. I guess another thing I'm involved with really is the agri-tech. You know, we know a lot of those additives actually just leave the polymer over time. So thinking about where they go would be quite interesting in the future. Mm-hmm.
Well, I set up BIFA. BIFA was my business. So, for rigids, we're not too bad. The thing about in recycling is we're actually, when it gets to the plants, we've actually got a massive averaging. So the one thing about post-consumer waste on rigids is we're dealing with a massive average. So each individual doesn't make too much difference. So the rigids. Films, much harder, because films are all about gel counts and those other properties, and all the different stuff in them really can create some issues. So rigids I'm not too worried about, it flows through. But we have films starting in 2027, and there are no film plants in this country. So getting films back into good products is going to lead a lot more work on additives and lack of additives and control.
Yeah. Okay, I think it's very challenging. Like people in the industry, sorry, it's too loud, trying to solve the problem that they know, and the fact is there's also some exceptions. For example, some contamination from consumer when they use the packaging for non-intended use. For example, my mom, so she has and it happens a lot in Asia, like she used the PET bottle to store gasoline. Imagine that, like, it happens all the time. You buy a bottle of, I don't know, some drinks, and then after you kind of use it, and then you kind of reuse it, like putting something in there, something that's not supposed to be in there. And yeah, that's contaminates our secondary feedstock, and yeah, that's the problem. I think the problem is that exception.
Yeah, brilliant. No, the reason why I asked that is because we know that there's going to be a huge global demand for secondary plastics, secondary polymers, and this is going to be one of the challenges for the next couple of decades. Right, we've got two questions. Brief, and who are you, Rebecca?
Hi, Rebecca Colley-Jones, Innis Resources. I just had a quick question, really kind of following on from that, around the new food contact regulations. And do you see that the novel technology routes is a way of being able to use our additives to actually encourage mechanical recycling of food contact products?
Oh, I've got wheels.
So first of all, in the UK, we're under EFSA, the FSA, who are even less resourced than EFSA. EFSA have never approved any food grade thing. So the first set of legislation I worked under for 13 years, and there's still no approval, and they've changed it. The novel technology is interesting if they change their attitude, because it should work on data. What we really want to go to is the US model. So the difference for people who don't know between the US and here is, in the US we have they give you, it's your responsibility, they give you a letter of no objection, which means we've looked at your process, we've got no problem with you, but you still get your pants sued off you if you get it wrong. In Europe, they've taken an authorisation approach, which means that EFSA, or the European Union, is taking responsibility and authorising your process. A civil servant has never taken responsibility, so there has never been an approval in Europe. And while that happens, if they can move towards the American model, which novel technology should do, then we might have a chance. Otherwise, no hope. Sorry, that maybe comes to question.
Thank you, James. Okay.
Hi, so my name's Ella. I work for Hexpol TPE. We're TPE compounders. So we're trying to utilise a lot of the mechanical recycled feedstock within our TPE. So my question is, there's a lot of new chemicals being added to regulatory lists and SVHC, for example. How can we ensure that the materials that are considered safe now will be safe in the future in mechanically recycled feedstock?
Cool, that's a good question. Who wants to pick that one? I'm gonna pick George first. Okay.
I'll go to George first because I talk too much.
Yeah, no, I think it's quite difficult, isn't it, really? So we couldn't make food-grade chopping boards because we just couldn't go down that route. I think that material's all stitched up for food packaging anyway. But that rather restricts what we can do, so we then have to look for other materials just to not have that level of risk. But, it's really uncertain that we've seen what the decomposition products could be. So it's a case of level of risk, risk-based approach, I would have thought, is many things that we do. So, yeah, I'm not sure. So it's rather good, that one.
Yeah, I think it's a big topic at the moment. We've been here an hour and no one's mentioned PFAS-free, but that's one of the main things. Yes, we can talk about having PFAS-free processing aids. What about the recycling you're going to add that's been made over the last 10 years? It's already in the chain. But I think without proper segregation, as I say, like, it's easier if you close loop, you know what's there, you know it's possible. But if you're having to add 30% and you've got to buy it from somewhere, it's going to be very, very tough.
It still comes back to, very briefly, when we built Biffa's food grade plant, which is the stuff you think, we took 2 tons of rejected gasoline bottles, everything else, and put it through the process and made it food grade. So 100% rejected bottles from the everything bad going through the Biffa process is food grade. So the issue on a lot of these things is not the actual quality, it's perception. At the same time, perception is important. So getting the quality fund, very briefly, a friend of mine in America wanted to make, did work on medical waste. And he showed that he could get food grade out of medical waste. And I said to him, Steve, yeah, and the question here is, how many people here would be happy to have food grade material making their butter dishes out of medical waste? Anyone happy? Okay, so there's a reality and perception, and we have to work in between the two.
Is that to do with scalability as well then? Are they small plant, like pilot studies that have done that, or is that a scalable process?
I've only ever done things on ton. I don't work anything less than a couple of tons an hour.
Yeah. Thank you.
Thank you very much. I don't think we've got time for one more question, unfortunately, unless it's a really quick one and you can get the mic over to that young lady very quickly. And whilst we are getting that, I'm going to just ask the panel to think about giving a very short statement about what are the no-nos in regards to contamination. But a very quick point or question.
Okay, I work for food manufacturing, so I buy the packaging. I can put additives in, my suppliers will put the additives in, it's all well and good, but the supermarkets won't accept it. So while you're sitting and talking about all of that, on top of that, you've got to get on the supermarket's approved list, because if you don't, no point.
I don't think you actually need to comment on that. I think that's a very fair point. Thank you. No, I think bringing in the whole supply chain is absolutely necessary. Really excellent point. Okay, this is really loud, sorry. So very quick final statement from all of you. If any of you are making or working in this space, what are the things, or what is the one thing that we shouldn't do to contaminate our future feedstock for secondary raw materials?
Well, people might say PET or something in polyolefin, but I don't think so. As a compatibilizer supplier, I think we can solve that issues easily. The thing that I think is a no-no contamination is something that we don't really expect, like cross-link gels from degradation or something like that. You know, once it's cross-linked, it means you can't really melt it, and sometimes even with the filter at the extrusion doesn't work well enough to kind of filter all this contamination out, and yeah, yeah, it's a no-no for me.
Very simply, it's collection. We can do miracles in recycling, but if we have a cleaner feedstock, we have to do less miracles. In Europe, they collect way better than we do. In here, we use the cheapest form of collection. We smash glass into our plastic, everything else. Better collection, slightly better feedstock, and we can do absolute fantastic stuff.
I just guess for me, it's just, can we avoid mixing the materials together? Do we have to have multi-layers, different polymers added together? Because that's a real problem for processing them into something new.
You've stolen my response. But yeah, I think simplicity is absolutely key. Less is more. So you're designing for mono material, you're putting as little additive in as possible, but making sure it actually has the right barrier effect, everything you need for your design.
Thank you very much. Thank you very much to the panel. That was a fascinating discussion, but also excellent presentations. Thank you to all of you for listening to the first session and for eating into your break. If you don't already know, the coffee is directly through the doors over to your left. If you'd like to thank the speakers in the usual way, we'll see you for the next session at around 11 o'clock.
Welcome to the second session of the day. I hope you enjoyed the first sessions. Lots of people networking out there, so there might be some stragglers, but in the interest of time, we'll try and get through to about midday, covering the session around green chemistry, the future, and the promise that the natural environment and green chemistry can move us toward a sustainable future for plastics. I'm your chair, and I'll guide us through the session. My name is Stuart Foster. I work for RECOUP. RECOUP is a UK membership-based charity who have been working on plastic circular economy, resource efficiency and recycling for what's coming up to 35 years. A lot has changed in that time, and some of the challenges that we're hearing today all here seem very similar as well. My only fee for chairing the session is just to let people know that our annual gathering and conference is a week today in Peterborough. So if you want to know more about that, just drop onto the RECOUP website and you'll find more details. I've got some notes here for the chair to read out, so I will oblige. Just to thank again the sponsors, Grantham Centre for Sustainable Future, Plastics Europe, and the Worshipful Company of Horners, who's made a kind donation to this event in memory of David Williams, and without them this event would not be possible, so thank you. In terms of housekeeping, there's still no fire alarms planned, so if it does sound, just follow via the nearest exit out to the car park, and the fire marshals will be waiting to point us in the right direction. A very interesting extra note on here is do not push the push here button. I don't know whether that's a psychological experiment, but it's there and don't push it. There you go. We've got a lot to get through. We'll try and stick to time. The speakers, I haven't spoken to all of you yet, but please do stick to your 12 minutes and we'll have a chance for some questions and discussion at the end. But without further ado, I'd like to hand over to our first speaker, who is Matilde Concilio from the University of Oxford. Matilde, over to you.
Yeah. So, hi, good morning. I'm Matilde Concilio. I'm a postdoc in the Williams Group at the University of Warwick, and today I'm going to show you some of the materials that we're making in the group, especially focusing on thermoplastic elastomers and reprocessable thermosets. So the expertise of our group is the synthesis of precise polyesters and polycarbonates using atomic efficient polymerization. So, for example, the ring opening polymerization of an epoxide with CO2 or an anhydride, or the ring opening polymerization of lactone or carbonates. And we use, like many of the monomers that we use can be sourced from renewable feedstocks. So we use these monomers, we then use atomic efficient reaction to polymerize them, and we then process them to obtain materials with specific mechanical properties. And the idea is that we design these polymers with in mind the idea that it can be then reprocessed, recycled, or degraded. So focusing on thermoplastic elastomers. Thermoplastic elastomers are based on blockopolymer structures, and the mechanical performances of their mechanical performances depend on the chemical composition of each independent block and also on the length of the blocks. So in our group, we can precisely control the chemical composition and the length of each block using a one-pot synthesis and switchable catalysis. And what does this mean? So in this case, in the example on the left, we have in the same reactor vessel, we have the lactone and the epoxide. We then use a single metal catalyst first for the ring opening polymerization of the lactone to form the first central block. And then we just switch the atmosphere in the reaction vessel from nitrogen to CO2 to then have the ring opening copolymerization of CO2 with the epoxide and get the two outer blocks. So using, of course, depending on the catalyst that we use and also on the monomer selection, we can achieve different chemical composition of each block. And we can also synthesize more complicated structure, like, for example, this pentablock copolymer on the right. So in this first example, we synthesize an old polyester-based thermoplastic elastomer with a soft central block of PDL, so polydecalactone, and two outer blocks of a polyester composed of CHO and PA that is more rigid. So to achieve the mechanical properties of a thermoplastic elastomer, we need to have phase separation between the hard and block domains. And this is achievable with the molecular weight of each blocks. And what we observe is that by reducing the volume fraction of the hard block, we have a reduction of the Young's modulus and also of the stiffness of the material, resulting in more stretchable material with a higher strain at break. And of course, another important property of thermoplastic elastomer is the elastic recovery. So we tested this, the elastic recovery, so the ability of the material to recover the shape after the elongation. And we tested after 10 cycles, and each material had an elastic recovery above 95% after 10 hysteresis cycles. We also synthesize a polyester polycarbonate thermoplastic elastomer and with a central soft PTMC block and two outer blocks consisting of VCHO and PA. And we confirmed the phase separation between the hard and soft domain using DSC, where we could observe two thermal transitions. The first one at low temperature corresponding to the soft block, and the second one at high temperature corresponding to the rigid polyester outer block. And what we observe when we tensile tested the material is we observe this clear upturn of the, this clear upturn of between 200 and 400% strain that resulted in improved mechanical properties with a stress at break close to 30 megapascal. And this behavior was attributed to the self-induced crystallization of the PTMC domain that are able to align and crystallize during elongation. But of course, advantage to have double bond in the side chains is the that we can further post-functionalize the polymer, and this is what we did. So to try to improve the mechanical performances of the material, we then functionalize the side chain with carboxylic group, and then we react the polymer with a zinc salt. And the idea was to have, the idea is that these polymers will have enhanced mechanical properties due to the stronger metal carboxylate interaction. And this is exactly what we observe. So in the case of the functionalized material with the carboxylic group, we have an increase in the stress at break, close to 40 megapascal due to the hydrogen bonding interaction in the hard block. But when we reacted with the zinc salt, we had like even better mechanical performances with stress at break close to 60 megapascal and an increase in the strain at break. And reversibility of this carboxylate metal interaction at high temperature also results in the reprocessability of the material that could be reprocessed several times without losing the mechanical performances. And of course, we use this strategy also for a different type of thermoplastic elastomer, where we have a central soft block of polydecalactone and two hard blocks of VCHO and CO2, so a polycarbonate. We then functionalize this polymer with carboxylic group, and we reacted the polymer with different salts to study the effect of the metal ions on the mechanical properties. And what we observe is that in the case of the unfunctionalized polymer, we have a very low stress at break, lower than 1 megapascal. When we functionalize it with carboxylic group, we have an enhancement of the mechanical properties with stress at break close to 4 megapascal and an increase in the strain at break due to this hydrogen bonding interaction. But the mechanical properties were significantly influenced by the metal ions. For all of them, we show an improvement of the stress at break, with the one containing the aluminum ions having like the greater increase in the stress at break, close to 10 megapascal, and this was caused by the trivalent nature of the aluminum ions. We also tested the elastic recovery of the materials, and we could observe an improvement of the elastic recovery when we functionalize it with the carboxylic group, and also in this case, the material containing the aluminum ions show the best elastic recovery. So we decided to take this sample and then test the effect of different metal content and metal loadings on the mechanical properties. And what we observe is that we could easily tune the mechanical properties of the material by just varying the content of aluminum in the sample. And with the material having the higher amount of aluminum ions having the higher stress at break and a slightly decrease in the strain at break. And of course, so the aluminum improve the mechanical properties, and also due to an increased cross-linking in the material. And this increase in cross-linking also leads to an increase on the second thermal transition of the polymer. And in this case, we can have a broaden of the operation temperature window of the material from -20 to 200 degrees. So if we compare the different strategies that we can use to improve the properties of TPEs, we could see that the use of this metal carboxylate interaction improve the mechanical properties more compared to other interaction like hydrogen bonding, stereocomplexation, or the increase in entanglement. But of course, we don't only make block copolymers in the group, we're also making just linear copolymers. And in a recent project, we've been working on the synthesis of low molecular weight polyester using commercially available and unpurified monomers that we then functionalize with carboxylic group, and we react them with a depoxy containing cross-linker in the presence of a mixture of two catalysts, the zinc octanoate and DBU, to form a covalent adaptable network with reversible cross-linking due to covalent dynamic bonds. And what we observe is that by keeping constant the concentration of catalysts, but changing the ratio between the two catalysts, we had tunable mechanical properties due to increased cross-linking density. and we have an increase in the glass transition temperature from -2 to 30 degrees, and this different thermal property also resulted in different mechanical properties, from a more elastomeric behavior to a more plastic-like behavior. And this material could be reprocessed several times without a significant loss in the mechanical properties. So to put all into context, in the Williams Group, we synthesize material that can cover a broad range of mechanical properties that can also, that often overlap to commercially available materials and plastics. But these materials have a high renewable content. We can tune the mechanical, the thermomechanical properties, and we have a broad range of operating temperature. And we also have in mind, always have in mind the idea that these materials need to be reprocessed, degraded, or recycled. I would like to thank, of course, Charlotte Williams and all the people that work on this project that I show you, especially I show you the work of Dr. Georgina Gregory and Mr. Kampoon, and of course all of you for the attention. Thank you very much.
Are there any burning questions you want to ask now? You're happy to wait till the end? Perfect, Matilde, thank you. Okay, I should have put a disclaimer at the start. I am not a polymer scientist, so this stuff fascinates me and scares me in equal measure. That also means I'm relying on you for the intelligent questions at the end. Okay, we'll move straight on. Next up, we have Richard Lambert from Braskem. Richard, if you want to come to the front.
Just is it this one?
Yeah.
Good morning, everyone. I'm Richard Lambert. Obviously, everything I share with you today is to the best of my knowledge. But I'd like to introduce you to Braskem and I'm Green polyethylene. First of all, Braskem, for those that don't know, we're one of the 8th largest petrochemical companies in the world. We are based in Brazil. Sao Paulo is our home, and this is where also our 260,000 tonnes I'm Green polyethylene plant is located. Just some points for where Braskem are in terms of our sustainable action pillars. Those 3 are social responsibility and human rights, eliminating plastic waste, migrating climate change. So, what's it like being the sustainable pioneer of bio-based polymers? Well, we have several initiatives going on currently at the moment. Braskem Siam is our Thailand operation, where we will hopefully build a new plant there in Thailand, which should give us another 200,000 tonnes. And then we have others, which is Sustainia, which is a bioglycols, and Kazulu, which helps that with its funding. Upside and Renew are our recycling initiatives, and then obviously what I'm here to talk to you about is the I'm Green polyethylene. So I'm going to cheat slightly, rather than spend minutes or hours trying to explain what I'm Green PE is. I'm going to put a video on. I hope it works. Bit quiet.
More than 10 years ago, Braskem turned to bioethanol made from sustainably sourced sugarcane, an alternative to fossil fuel, in order to produce I'm Green bio-based plastics. Once harvested, the sugarcane is brought to a mill to be crushed and converted into sugar and bioethanol. The leftover cane is then used to generate renewable electricity. Sugarcane captures CO2 from the atmosphere. This means that for each tonne of I'm Green bio-based plastic used instead of fossil, around 5 tonnes of CO2 are avoided. With this, Braskem and our partners are making a positive contribution to sustainability and carbon neutrality goals. Braskem requires strict environmental and conservation standards from our bioethanol supply chain. Together, we developed the Responsible Ethanol Sourcing Programme, which establishes operational and sustainability standards, fostering continuous improvement. The programme also covers socially responsible working conditions, including commitments on labour, wages and health and safety. Sugarcane production contributes to the restoration of degraded pasture land in the south of Brazil, more than 2,000 kilometers from the rainforest. Plastic made from sugarcane is also recyclable within existing recycling streams. So at the other end of the circular economy, green bio-based products can be recycled and turned into new products. Just like the sugarcane processing, we maximise value, bringing to life the bio-circular economy. Together, we are on our journey to create a more sustainable future today.
So hopefully that saves me some time to try and explain it all. But I'd like to concentrate on some of the points behind this. Obviously, Brazil is a huge country. It's some 850 million hectares of land. It's quite a big part of the world. Sugarcane plantation is some 1,500 kilometres. That's probably the closest, biggest plantation closest to the Amazon. And the Amazon is obviously one of our first questions we always get asked about. Are we deforestation of the Amazon? The answer is simply no. And the reason for that is as you can see there on the map, the Sao Paulo state is where the majority of the sugarcane is grown today. That accounts for some 87%. That's actually some 2,500 kilometres away from the Amazon. And the reason that's the main plantation is there is because of the land. So you can't actually grow sugarcane in wet land. You need dry climate land where also you get the rain. So we get the rain from the west and the sun from the east, which gives Sao Paulo state the perfect place for growing sugarcane. Also, you'll see in the top right, which is Bahia in the northwest. That's probably the second largest one after that, which is some 2,000 kilometres away. So there is no deforestation for sugarcane. We also have an agrological zoning programme, which I can touch base with people offline. That covers some points that we obviously need to adhere to, which are really main areas for proper conditions for mechanical harvesting. So there's no sugarcane burning, which is something of the past anyway. Also to ensure that we grow the material on degraded land. That's quite an important part of the of this as well. But again, I can touch base with people on that after. So land use. This is also one of our big questions. How does that look like? Well, just to give you an idea, as you can see in the top middle centre there is the sugarcane. That's 8.3 million hectares of land. As I said, Brazil is some 850 million hectares of land in the first place. So from the agricultural land, I'll start again, actually in the farmland at the top, you'll see is 282 million hectares of land, of which 118 million hectares is used for agricultural, of which 8.3 million hectares is for sugarcane. Just to give you an idea of scale, what does 8.3 million hectares look like? Just to grow sugarcane on, it's the size of Portugal. So it's a huge, huge area. So how much do we take from that? Well, actually, as you'll see in the graph, we actually take 0.03% of Brazilian land for sugarcane, but actually the ethanol which we take is less than 1% of land that we use of the sugarcane. Sugarcane is, I'll cover it in the next slide, it's a very robust crop in Brazil. Two main things, firstly sugar, second is ethanol. I'll come on to that shortly. Then the other important part of it, which you'll see, is the 164 million hectares of pasture land, of which 34 million hectares is degraded land. So that's where cattle has been, gone, moved on, and that's again part of the Brazilian agrological, can't even say the word, zone, which is something we need to concentrate on. And that's 34 million hectares of land. Again, just to give you an idea, so that's degraded land, which we could grow on if we wanted to, is the size of Germany. So it's a huge area where the sugarcane growth could come from. So how does it all work? Well, as you've seen in the video, it's actually very simple. We harvest the sugarcane. Just to give you an idea, a hectare of land, if you like, we harvest that once a year. So sugarcane is actually, it grows like grass, so it grows very easily. So the moment you chop it at the root, it starts to grow again. So within a year's time, we can then harvest again. And what we simply do, using mechanical harvesting now, is then take the sugar cane to the sugar mills. I think there's some 400 sugar mills in Brazil itself. And then we simply crush it. The first crush is used for sugar, and then the remaining crushes we tend to take the ethanol. You can't, well, it's 1 or 2 squeezes for sugar, but after the second squeeze, the juice, as we call it, isn't actually good enough to process sugar anymore, which is why in Brazil, for some 70 odd years, they've actually then turned that into ethanol, and then bioethanol, which obviously is used for the cars in Brazil today. So it's a cogeneration product. 1 is sugar, 2 is ethanol, and then actually the one I like the most is called bagasse. So bagasse is the product which is left over or the waste of the sugarcane crushing. And actually what we do with that, we actually incinerate that. And the reason for the incineration is because it gives us a huge amount of energy. So that powers, so when we take the bagasse, it powers 30% of all the mills, of the mill itself, and then the remaining 70% is then sold back to the grid. Bagasse in the industry in Brazil actually accounts for 16% of the energy. So it's a huge energy factor for Brazil, which is sold to the electrical matrix. The whole process is also taken. There's other things in there, vanasse, for example, and the filter cake, and then also the ashes, which is the remaining of the bagasse, we actually put back into the field, which actually acts as a pesticide and also as a fertilizer, which actually reduces our fertilization by 60%. So it's actually a huge impact, plays a huge part of the process. So why do we do all this? As it says in the video, it's actually to carbon footprint, to reduce carbon footprint. Sugarcane captures lots of CO2, and at the end of it, we end up with minus 2.12 tons of CO2. This is for high-density polyethylene. Low-density polyethylene is slightly higher at minus 2.27, and linear low density is 1.89. Again, I can cover those with you offline to go through those with you. But essentially, the difference is 5, because using fossil fuels for petrochemicals gives us a carbon footprint of +3 today, globally. So actually the difference is 5. So it's a huge way of for brands and companies to reduce their carbon emissions by using the sugarcane and green. Then also just something that, just to cover, we have our own responsible ethanol sourcing program. This is basically it used to be our code of conduct. However, we ensure when we buy our ethanol, we're buying it from those companies that first of all take the sugar, and then obviously comes the ethanol for sugar cane. So, short and sweet, but I'd like to thank you for your time. Obviously, welcome to any questions, and thank you to GRIPS for allowing us to present today. Thank you.
Thank you, Richard. That was excellent. And I think bio-based has been around for a while, and we've heard it. And you know, some of our members, certainly the Cokes, Danons of this world, and so on, they've seen it for a while as a good opportunity. Again, if there's any critical questions, we can take them now. I am the microphone runner as well, so if you take that one. And if you are asking any questions, if you just tell us who you are and keep it concise.
No problem. Thank you. Hello, I'm Brian. I'm from Oxford. I am building a technology to recycle waste plastic to propane and ethane. I'm asking, my question is about chemical recycling. How does petrochem industry, for example, in Brazil, like Braskem, how do you guys see chemical recycling as the route to recycle plastic to a higher level of purity?
Yeah, good question. Well, I think like most materials, there's no silver bullet today. That's the first thing we should state. Obviously, every product has its means and usages. So chemical recycling is something that we also have in our product and portfolio. And yeah, it has its place. There's lots of challenges with chemical recycling at the moment in terms of mitigation, food use, all the all the questions that we know that need answering. So currently, yes, we are invested in chemical recycling. I think our current capacity is around about 200,000 tonnes.
And I'm just looking, I think there's more depolymerization sessions later today as well to tune into. So that probably has a bit more info as well. Any other questions, sir? We'll take these two and then we'll move on. And at the end, we can pick those back up. So,
Hi, Rob McElroy, University of Lincoln. The ash from the bagasse, do you know what the metal content is in there and the silica content? And have you thought about other uses other than, or that complement the fertilisation?
Great question. I'm also not a chemist, so I don't know. But I'll find you the answer for you, and we can take it offline, no problem. I'll swap cards with you at the end.
Hi, this is Amir from Wernicke. So a quick one. I got a bit confused. I get confused very quickly, actually, sorry. But you produce ethanol to be used for producing your HDPE, right? And ethanol is bio-based, that's it. So ethanol is bio-based, not the plastic itself.
Well, the feedstock has come from sugarcane, which is the bio-based content. So all our products have bio-based content in them. The HDPE has 96% bio-based content in it. LD is 97%.
What is that content? So from the sugarcane, is it which part of? Just I'm a bit confused. Sorry.
So we take sugarcane, and then from sugarcane you get sugar, and then you also take the ethanol. We take the ethanol, we dehydrate the ethanol, and that ethanol is then turned into ethylene, and then the ethylene is turned into polyethylene. So the feedstock is the sugarcane. I hope that makes sense.
perfect. Thanks, Richard. I'm sure there'll be more questions a bit later. Thank you. Okay, next up, we move on to Mattia Parati from Flexsea. Mattia, over to you.
Good morning, everyone. My name is Mattia Parati. I apologize for my voice. I'm getting over man flu, apparently. But this morning I will be talking to you a little bit about what we do as Flexsea and a little bit about our chemistry as well. Definitely not as complex as Matilde's talk. We're not as clever as her. We're just merely cooks. We're formulation scientists. We're not chemists properly. But yeah, Flexsea focuses on using sustainably cultivated red seaweed to produce home compostable seaweed-based materials, both in the rigid and in the flexible space. There is a problem, though, with some bio-based feedstocks, and the speaker before me did a very good job at showcasing how you can use the whole feedstock to extract sugar and then valorize the ethanol as well to make the full process circular. And we try to do exactly the same with seaweed. Conventionally now, seaweed hydrocolloids comprise between 10 and 30% of the seaweed, and they are used as food additives, as thickeners, emulsifiers, additives, and so on and so forth. At Flexsea, differently from other bioplastics company, we want to use 100% of the seaweed. And what we do is we take the extraction byproduct as well, and we reconvert it into different biomaterials that we can either complement our plastic or that we can have other uses for as well. Today specifically, I want to talk to you a little bit about some of the problems that we have overcome to ensure that we can have a solution that is both a rigid material as well as a flexible material, and that is to do with plastification. So, as I said, we're not very clever chemists. We just looked at what people did with thermoplastic starch, in which they took starch, which is a carbohydrate, and then they plasticize it with sugar-based plasticizers, fundamentally. And differently from seaweed hydrocolloids, starch-based materials are a bit more complex because they are comprised of amylose and amylopectin. It's a branched molecule. It's a bit more complex. It's a bit more crystalline as well. So it's a completely different. It's a similar system, but it's also quite different. And so what they did essentially there is the fact that you have different stages in which first you break down, well, you don't break down, you just change the physical interaction between the chains of the amylose and amylopectin, and then you add plasticizer in there so that you separate the chains slightly. And what that does fundamentally is that it gives you the ability of the material to actually flow. And essentially becomes a thermoplastic material. So you can melt it, you can process it, and then you can harden it in injection molding to create a rigid material, or you can make films out of it, and so on and so forth. Beautiful material. So the concept of what we do in extrusion, and I don't want to get too technical, but essentially what we're doing is we're feeding a material with starch, we're feeding a material, we're disrupting the crystalline regions of that material, we're adding a plasticizer, we are removing the moisture from the material, we are compressing the material, and essentially we are, after we have rearranged the chains of the material, we're extruding it to form a final product that hopefully is not very crystalline anymore, is quite plasticized, so we can then reprocess it. So why did we want to work with seaweed-based materials? So what are the main drawbacks of thermoplastic starch? First and foremost, it's only industrially compostable because of the very, very complex nature of the material and of the molecule, and it's very big. So it takes a long, long time for microorganisms to degrade it, and it only degrades mostly in very high temperatures, so in industrial composting facilities. The whole reason of argumenting between land used for crops that we then use, we take food for, or the land that we need for actually making commodity materials. Retrogradation is quite a big issue with thermoplastic starch, meaning that we have disrupted the chains, we've plasticized the material. Over time, some of that plasticizer or those chains may move, and so the material becomes crystalline again. So it changes properties, yeah? So it's not a material like plastic that it will stay the same if put on a shelf for 100 years, yeah? That's, yeah. High hydrophilicity. This is a main drawback of bioplastics. Bioplastics, by definition, need to interact with water to degrade, yeah? So we're trying to kind of solve a problem that we don't want to solve. So not have too much hydrophilicity, yet still be very hydrophilic. So when you put it into a composting facility, then it will degrade. With thermoplastic starch, you have very opacity is one of the issues that you have. You don't have full transparency of the material. To make films for making windows of pasta packaging, for instance, which we're now thankfully removing, or similar applications to those, you need to have transparency. And you also have quite a complex system because you have an amylose and amylopectin. Different plants or different sources of starch can have different contents of those two materials. And so what happens is that you have very high variability, which means that you have to standardize your process better. And that is another drawback of some of these bio-based materials. The beauty of what we are doing is that agar and carrageenan, which are two of the main products, hydrocolloids from sustainably cultivated red seaweed, they have been around for 50, 60 years, and they've mainly been used for the food industry and the pharmaceutical industry. The main kind of pivotal point of that is the fact that you need to have very, very, very high reproducibility of the material, your main feedstock, which is what we have. So we know batch-to-batch variability is not a big issue. Hydrocolloids, much smaller molecules compared to amylose and amylopectins. They're not branched, so they're linear molecules. So technically, you should be able to plasticize them way easier. You don't have, because they're not as big and because they're not as branched, you don't have initial crystallinity of the material, which means that you don't have retrogradation, so they don't go back to, they shouldn't change properties over time if you leave them on a shelf, that is. And another important thing is that, I forgot. It'll come back to me. So some of the benefits, monomaterial, yes, this was it. So it's repeating blocks of the same units, so you don't have ratios between amylose and amylopectin, for instance, yeah? So monomaterial, higher purity, we can get that purity, we can standardize that purity over batches. Smaller chains, home compostable. Sustainably cultivated, where you cannot cultivate anything else. In Indonesia, usually you use ponds, which are very, very salty. Not even fish want to be there, but seaweed will. It's an amorphous material. We can get incredible transparency, and I mean incredible transparency with our films. You can have theoretically improved interaction between the plasticizer and the polysaccharide, which means that you can tune the properties a little bit better compared to thermoplastic starch. Challenges to overcome: hydrophilicity. That's the reasoning, that's what I was talking about earlier. You need to have a hydrophilic material for it to degrade and for it to be home compostable, yet you cannot have too much hydrophilicity that if you leave a pot on your desk, it absorbs that moisture, changes the properties, or whatever it might be, the changes in there. You need to have very good processing. So the combination between temperature, shear, viscosity of the material. Carbohydrates are not thermoplastics to begin with, so that means that they don't melt like thermoplastics. They might have a thermoplastic-like behavior, which is what we like to call it, which means that it's a combination between, you can induce melting based on shear and temperature, not only one, not only the other. So usually conventional thermoplastic, you just apply temperature and you melt the material and it will flow. Not the case with our material. So finding the perfect blend between mechanical properties, barrier properties, processing is quite a big challenge that we had to face. And that's why we're 3 years in and we're just about to go commercial. So I want to talk to you about some of the strategies that we tried. And I don't want to tell you our secret on how we achieved it, but yeah, it's not a huge secret. I'm happy to talk around it, if you like. I'm by no means a good drawing guy, so I apologize for this. But some of the applications that we might want to put our plastics in, they might want to have increasing hydrophobicity, so higher hydrophobicity. And for that, you can have your material that is plasticized, and you can add some hydrophobic components to it, like, for instance, proteins. Yeah, proteins, you can find very nice hydrophobic proteins that can give you potentially better properties. However, you can have, because you have a hydrophilic matrix, and then you have a hydrophobic component, you can either disperse it, but you might have some incompatibility of the material. Yeah, so you have to overcome that incompatibility somehow. Again, our material is home compostable, so and is naturally derived. We don't put any chemically synthesized materials. We had to get very, very clever in doing this. But we do have different grades of different materials that have different ranges of hydrophilicity and hydrophobicity. Differently from thermoplastic starch, starch is, as I said before, bigger chains, longer chains, like high-density polyethylene, for instance. Bigger chains means you have more strength of the material, yeah? So our material is not particularly long chains, so if you want to increase strength, one of the very good ways and very simple ways to do it is to increase fiber content. However, you can increase fibers, and like cellulose fibers, they're very crystalline, so you are going to disrupt your amorphous phase quite significantly, which means your processing is going to be completely different of the material, your plasticization is going to be completely different. So that's another parameter to have a look at as well. So that's another thing that we've had to play around with. You can, for different applications, if you want to go more towards the TPUs or the rubber kind of materials, you can try to increase flexibility and elongation. Again, if you add simply more plasticizer, well, after a bit, you don't have any more interaction between your hydrocolloid chains and your plasticizer, which means that you have an abundance of plasticizer flowing around in your system, which means that the plasticizer will migrate from inside the system to outside of the system. You don't want to pick up something that is sweating an oily substance, even though it's just food-grade plasticizer. It doesn't matter. It's not good enough. Consumers have now understood that plastic can be perfect, which is great, but it's not great for solutions because you've got quite a high bar to try and compete with. The other big issue that you have with home compostable material or bio-based materials in general is the fact that your price points are going to be quite higher compared to a conventional virgin plastic polymer. So what the standard thing to do is you can add fillers in there, and you can still obtain and you can still have home compostability even with a significant amount of fillers in there. We are not particularly keen in doing that, but there is some fillers that you can add in there. You can add fibers, fillers. Some of these fillers, like for instance calcium carbonate, they're incredible nucleating agents. If you want to crystallize some materials or some other additives that you can add in your product, so you can again change your processing temperatures, your parameters, your viscosities, your cycle time if we're talking about injection molding, and so on and so forth. So that's another thing that we've been playing around with. And then you always are required by your customers to be able to expand the target market and applications. Oh, could we use it for this? Oh, could we use it for that? Oh, could we use it for 3D printing? Or could we use it for that? And every single application really needs a lot of fine-tuning because the reprocessing properties or temperatures or parameters are going to be significantly different to one another. So you really need to be on your toes, and the formulations will have to vary without a sign of a doubt, which might not be the case for most virgin polymers. And this is an extra cost, an extra challenge when you're trying to bring these materials to the market. So yeah, how are we sustainable in terms of both raw materials and cost? Valorizing byproducts, fundamentally. Not our byproducts, but what comes upstream from us. So those that extract the hydrocolloids, those that extract the process the seaweed, they already have quite a lot of materials that they don't use at the moment. They landfill, they chuck away. Most extraction companies actually have to pay to take away some materials that we can make other materials with, and it's mind-boggling. But this is the new generation of third-generation materials for biotechnology and bioprocesses. By the way, I'm a biotechnologist by trade, so I've got my PhD in biotechnology. So that's when I joined the company very early on. This was my bit to the company, and I then learned how to make plastics, but that's another story. Thank you very much for your time. Any questions? I'll be around all day, so if you want to have a chat, more than happy to have a chat. If you want to email me, my email is up there. And yeah, thank you very much.
Thanks, Mattia. Any initial questions you want to...
What's the supply potential of seaweed as a resource, just thinking about scaling this up?
Yeah. So today, cultivation of seaweed is quite significant in the Asian continent already. It's been expanded to Brazil, amongst other, and Africa. The beauty with sustainably cultivated seaweed is that it's a crop like sugarcane, that you can just cut and it regrows, and you've got a 45 days cultivation cycle. You can increase your year-on-year supply of the seaweed you can double the supply year on year if you wish to do that. Today, the supply of seaweed is something about 70 million tons of raw material, something like that. Yeah.
Thank you. We have two more, and then we'll move on to the next speaker.
Okay, back to a question I asked sort of earlier, right? This is great, but you're going against every single supermarket's packaging policy. So if you're going against the supermarket's packaging policy, we just cannot touch it.
That's fine. Supermarkets might not be our target market for now. Your policies will change, our material will improve, and we'll be able to enter new markets as well. Plastic supermarkets are not the only customer for us either. So we really want to make an impact. So we want to work on single-use materials that need to be composted. I would rather supermarkets recycle more of their material, use more recycled materials rather than our material. Our material might not be great for most of our supermarket applications or products. So Yeah, I mean, there is a long way to go before we can get to supermarkets. I mean, these technologies have been around for 5 years, 10 years. How long has plastics been around? So we don't even know if we can be suitable for some of the shelf life conditions and supply chain conditions that supermarkets will require from us. So yeah, you make a great point. You're completely right.
Thanks, Huilo from University of Surrey. I'm glad you talked about shelf life. So that's my question. How long is the shelf life?
It depends what you're trying to package in that. Specifically for our most standard hydrophilic grades, if you're packaging in their oil, waxes, waxy deodorants, soaps, you're talking, and you're storing them in a normal kind of even high humidity conditions and high temperature conditions. You can have months, a lot of months, 18 months, 24 months. We're doing testing now with quite large partners that are interested in that, and we've got a smart grant on that as well. So we're testing that as we speak, but I would predict anywhere between 12 and 24 months, depending on what you're storing in there.
Thank you.
Thanks, Mattia. We need to move on now.
Yes.
So the final speaker of the session, pleased to introduce Dr. Sally Lawrence from Polymateria. I'll just double check the slides work for you.
Is it a clicker?
Perfect. Yes. Lovely. Over to you, Sally.
Thank you very much. So thanks everyone for having me today. It was really great to hear the first three speakers speaking about specific innovations, and I'm going to speak a little more generally about what to do when you have an innovation and how to successfully implement new innovation. So first of all, why do we need innovation in the plastic space? And the answer to that is really around plastic pollution. I'm sure you're familiar with some of the numbers on this slide. It comes from the Ellen MacArthur Foundation, but we make a huge amount of plastic every year as a society. And in terms of plastic packaging specifically, we make about 78 million tons a year. Now, unfortunately, only about 14% of that is collected for recycling, and less still is recycled, which means that we have about 40% going to landfill, which is a tremendous waste of a valuable material. And more unfortunately still, we have about 32% of plastic packaging being leaked into the environment. So we need innovation. We need it across the value chain. As Richard correctly said, there's no silver bullets here. We need innovation in waste collection. We need innovation in recycling. And we need innovation in that end-of-life leakage into the environment. So, okay, we need innovation, but a really important aspect of innovation is we need to commercialize it to make it successful. In order to move the dial on this waste issue that we have, we need lots of solutions actually being implemented in the real world, and we need to avoid the terrible valley of death that I'm sure many of you are familiar with. So, how do we do that? I like to think about asking yourselves the right questions in order to set yourself up with a foundation for success. So I'm just going to talk to you a little bit about the questions that I like to ask myself when trying to bring in new innovation. Now, first question you should ask is, what's the existing landscape? What are the alternatives to what I'm doing? And finding that distinct area where you offer a key value proposition that's better in that specific area. The second question that it's really important to ask yourself is, how do I demonstrate that technical credibility? You'll probably know your innovation really, really well and really understand it better than anyone else. But what are the key pieces of data that you need to demonstrate so that you can show that to the world? And then finally, how do I tell my technology story? As scientists, we tend to be great at talking to other scientists. We love talking about our really technical stuff, but it's also really important to actually get to decision makers and to be able to scale up your technology is, how do we tell our story to non-subject matter experts? So I'm going to run you through how we've answered those questions for ourselves at Polymateria. So first of all, I guess I would just point out that Polymateria was founded as a purpose-driven organization to deal with the issue of plastic that's leaked into the environment. Of course, when it comes to plastic pollution, we want to start with that hierarchy of needs, which is reduce, reuse, recycle. But we were founded with the issue of if that doesn't happen to that material and it lands up in the environment, can it be made biodegradable, specifically to polyolefins? So what we did was we looked at that biodegradation sort of landscape and looked at what are the alternatives out there. And with that in mind, we divided it up into what's the managed waste stream and what's the unmanaged waste stream. So in the biodegradability landscape, in the managed waste stream side of things, we have polyolefins that are biodegradable with landfill gas capture. That has applicability in certain jurisdictions, maybe in the US, where they're bringing in rules around new landfills having biogas capture. Maybe that's a solution that would work there. Industrial composting, in certain situations, that's a great solution, especially where you have the facilities that are needed to do that industrial composting. And it was great to have our last speaker speaking about home composting. I've always tried to be an avid home composter myself, and that works well in suitable climates. Our focus is on the unmanaged waste stream. So that's where we see our different value proposition. Our alternative is when polyolefins get into the environment, can we make them biodegradable so that they will return to nature and have no impact? So we've established what we believe to be our key value proposition. So the next question is, how do we show that to the world? How do we demonstrate get independent verification and demonstrate technical credibility so that we can explain our data? Now, first of all, of course, you're probably going to develop your technology in-house because that's the way we do it. But there are many great organizations out there. There are many great academics. We should leverage the skills and the knowledge of academics out there to help us with that technology development. Once you've developed your technology, it's really, really important to look at what's the standards landscape and how can I demonstrate the right data to show pass-fail criteria, to show that the technology works. And really, really important is to do that at third-party labs so that you're not marking your own homework. And, at Polymateria, an example of a local specification that we need to follow is PAS 9017. If you're in renewable feedstocks, you might be more looking at ISC C+ certification. Once you've done that, patenting. It might seem on the surface of things less about independent verification, but what patenting does offer is that the patent examiner will do a search regarding the prior art. Now, you've probably done that yourself as well. If you're an innovator, you probably have a good understanding of the prior art, but the patent examiner will also do an international patent search if you file a PCT application. So that'll just give you that opportunity to verify your thoughts in terms of the prior art and your unique technology. And finally, and this last one is my favorite, and that's peer review. And I think that's one that's underutilized generally in industry, and particularly when you are an SME. We're really, really time crunched, we're really, really resource crunched. So it's hard to take the time to do that publication. But what publication offers is peer review. And when you think about it, it's really a gift. You have excellent, experienced scientists who are going to take the time for free to look at your technology and give you feedback on your science and maybe give you some insights in terms of how to do things differently. So that's something that is really, really valuable tool for us all. So, okay, you've figured out what your unique space is. You've demonstrated that technical credibility externally. So the last thing you need to think about is how do you tell your story? And really you need to think about 3-minute elevator pitch to people who are not subject matter experts, but they could well be the people who could unlock the decision making and the access to finances that you need to scale your innovation. So I'm going to give it a go to tell Polymateria's story, and I don't know, do I even have 3 minutes? 3 minutes or less, and we'll see how it goes. So at Polymateria, we developed master batch technology that integrates within the polyolefin landscape to create materials that are then biodegradable polyolefins if they escape into nature. And this is integratable into the existing value chain. So you don't need new capital assets, you don't need new capital investment. You can just, this is an operational change that you need to make. Once the products have been made, they actually have the same mechanical properties. We've measured these with all of our customers. There's no change to the mechanical properties. There's no change to the barrier properties of that polyolefin. However, at the end of life, we offer two different scenarios. We have studied extensively the impact of these products in the recycling stream, and there's no impact to the process or the products. And we have an examples here of some products that we've made using our technology. Unfortunately, however, as we know, a lot of plastic leaks into the environment, particularly in certain countries in the developing world where there is no waste collection. And in that case, the solution will biodegrade to nature. This is an example of a biodegradation graph where you're looking for 90% biodegradation. Here we have it in under a year. The material will biodegrade and leave no trace behind. So that's our story, and you know the challenge I would set for you is whether you're innovating in a large company and you're trying to get decisions made from your leaders, or whether you're a small company trying to scale yourself. You know, how do you ask yourself what's the unique proposition that you're offering? How would you validate your technology externally, get independent verification, and yeah, you know, really looking forward to hearing your stories about the innovations that you're creating in the coming weeks, months, and years. So with that, I would just like to acknowledge the people who actually did the work. One of them has surprisingly showed up today. He's no longer with Polymateria. So that's the innovation team at Polymateria. The funding agencies that make a lot of it possible for a lot of us to get started in this space. I'd like to thank GRIPS for having me, and I'd like to thank you for listening.
Thank you. So if the speakers could make the way to the front, and it looks like quite a comfy sofa over there, so make use of it. Any specific questions for Sally while we're doing that?
Hi. Sally, sorry. It's about the innovation process.
Sure.
You're saying about, obviously, the first stage is understanding what's already gone before. Now, quite often, a lot of failures are never out there. So actually, you could end up on a journey that somebody else has already tried and tested, potentially 3, 4, 10, 20 times, and just come to the same conclusion. But because it's a failure, it doesn't get out there. Mm-hmm. What do you think needs to be done to sort of address those sort of issues so we don't keep repeating mistakes and make sure that the funding is put into things that takes it forward?
That's a really good question, and I didn't think about that at all. You know, when I was working on that. So thank you for that question. I would say you're right. It is tricky. Sometimes you can see what area people have been working on from academia, and I think a really important aspect there of finding what's not published is networking. You know, seeing who's working in the space, who can you talk to them about their failures and find out what they've done, getting out there and learning about things. And I would say that the other thing that we need to try and do as innovators is think about how we fail fast. And in that regard, I think, you know, what's the smallest scale on which we can answer questions? If I had talked about further on towards that valley of death, I would have talked about how you address scale up. What are the questions that you need to ask and answer? They might be about kinetics, they might be about mixing. You know, I'm not a chemical engineer, but this is where it's really good to have a chemical engineer who can ask and answer questions about that scaling process, because you want to make your mistakes on the smallest possible scale. A plug, I guess, for the University of Liverpool. They have the Materials Innovation Factory where they have fantastic automated kit where you can do lots and lots of experiments on a really, really small scale. And then you can use digital tools to create models and sort of look at your space in depth without having to do thousands of experiments. So those are some of, those are the things that come to mind off the top of my head.
Thanks. If you want to join the other speakers. So any general questions from the session? I just wanted to build on what Sally was just talking about. So we know decarbonisation's a key element of sustainable future. Yes, that graveyard and the areas of issue. So I think actually across the piece, in terms of how far the technology is moving forward, what is the bigger challenges? And just unpack a bit in terms of what's stopping the scaling up, and what kind of timescales are you hoping for, and what kind of timescales do you think are realistic to really make a dent in that fossil-based plastic production, which I think this year is peaking at about 400 million tonnes globally. So it still feels like the new solutions have got a fair way to go.
Yeah, so from our side, it's well, we have scaled up. We're already at 265,000 tonnes. We have another 200,000 tonnes we can get to. We're trying to get to 1 million tonnes of bio-based materials. That's from a whole host of different chains, bioglycols, as I mentioned earlier, as well as the biopolyethylenes. So I think our biggest challenge today is actually legislation amongst brand owners and how actually we account for carbon and how carbon footprint is reduced. That's probably our biggest challenge today.
I think in my case it's probably the cost of the materials and the catalyst that we're making. So, but of course, if the legislation, the policy changes, then you're kind of forced to make the changes and to more sustainable material. So that at the end would be not just such a big of a problem.
Yeah, great question. So I would answer that in two ways. Like Braskem, we are at commercial scale, and similarly, that sort of regulatory landscape needs to catch up. Often the innovation comes ahead of the regulatory landscape, so that really needs to catch up so that there's an understanding of how to assess the technology and how it compares and where it should be used. When I think about Matilde's material, and when I go back to my previous life, I think an issue for a lot of people scaling is access to pilot facilities. Because when you want to go from a lab scale, say 10 grams, 100 grams to 10 tons, 100 tons, if you look at petrochemicals, we're making hundreds and thousands of tons a year. You need to be able to do kinetic studies and see the impact of equipment on your reaction, and to do that you need access to pilot facilities, and they're very, very expensive for a new company or an academic to do. So I think that's something that's really key for scaling innovation.
I kind of tie into that as well, because for us we did, because we're in the UK and it's such a great landscape to do innovation, we did get access to quite a few pilot facilities. However, it's different pieces of equipment, and that gives you inherent variability in your results. So reproducibility then is really key to then try and understand that. I mean, for us, it's just the understanding that we are trying to do something that in plastics it's been done in 100 years of optimization and engineering and having a lot of clever people thinking about it. And for us, it's one of the few startups that are starting to begin in this space. And it's just the understanding of how much money needs to be put into actual innovation to be able to get to anywhere meaningful, to give disruption really in the marketplace. Yeah.
Make a good relay team with the baton passing. Okay, so final question, because we do need to stop for lunch then. And making it slightly political, there's a lot of data and evidence, so, and being selfish as well. So in the UK, there's a new government. I think UKRI have got various funding pots, and we're looking at ways forward. So what would be the specific ask then, if policy legislation support would be required from the UK government to try and make the UK a hotbed, if not the world leader in this kind of development? Go down that way.
Yeah, in my opinion, is really kind of investing in scale up. UK wants to be, again, as to my understanding, an innovator in raw materials and being able to provide a lot of solutions and high-end solutions in the marketplace. Well, you need to invest a lot of money to be able to do that and incentivize research in that aspect. So that's the big ask, is just investing in very big projects of scaling up from kind of the hundreds of kilos to kind of the hundreds of tons, which is what plastic industry needs to have, and many raw material industries as well. But also not overlooking the very small guys. When you start out exploring an idea, those £50,000 grants, they are really lifesavers, or they really give something to companies, and yeah.
So I guess I'd answer that question from a funding perspective, and I'll answer it, you might sense that I have a bit of a weird accent because I lived in Canada for 20 years and moved back to the UK in 2022. And something that has struck me since I've returned to the UK is the complexity of the funding landscape, that it's all these different calls. And so you have to write a different grant application to address these different questions every time. And I've spent huge amounts of time applying for 100 grand. And you're like, God, like that doesn't go that far when you're doing chemistry. Whereas if I compare that with the Canadian landscape, it's very streamlined. There's not all these funding calls. It's just, this is the funding body. This is how the application works. It's always the same form. So you fill the form out once and you get it or you don't. And there's basically sort of 3 different funding bodies, 3 different types of grants. So it addresses your point around, are we at small, are we at medium, are we at large? But you're not sort of just spending so much time answering different questions, and it's like kind of the same stuff, but in a different way. And that can just feel inefficient to me.
I totally agree. I think it's mostly, the investment also in building relationship between academia and industry to make easier this transition from a lab scale to a more like an industrial scale. And and also to really understand what industry wants from the academia. So I think it's just the investment.
Yeah, then from our side, again, legislation is really, it's accepted in Asia or Japan specifically for bio-based plastics to be in the polymers and in the products. In terms of the European Union or PPWR, I think the Dutch are leading the way so far. They're talking about bio-based plastics and or recycling plastics at 30%. So you can have one or the other. So I think that's something that the UK could potentially also get on board with. Again, material can be used with recycled or bio-based materials.
Thank you. And on that note, I know some people from the British Plastic Federation in the room and with the UK Circular Plastics Network as well. Maybe some of those messages can be passed through. So that's it. We've run out of time, unfortunately. Fascinating session. Hopefully you've learned something. It's driven a bit of inspiration or challenge or given you some ideas to move forward on. I'm sure the speakers will be around at least for lunchtime, if not into the afternoon, so please find them. And just enjoy your lunch, enjoy the rest of the day, and just thank once again the speakers for their excellent contributions. Thank you.
Good afternoon, ladies and gentlemen. I hope that you can hear me at the back. Good. I'm afraid that there's a lot of bureaucracy to get through when you're the chairman of an event. So for starters, I'd like to extend our gratitude and thanks to the sponsors of today's event. That's the Grantham Centre for Sustainable Future, Plastics Europe, and the worshipful company of Polymers, who made a very kind donation to support the infrastructure of the event, in memory of David Williams, who famous figure in the UK plastics industry. This might be better. And, without them, the event would not be possible. So many thanks to all those organisations. In terms of fire alarms, there is no fire alarm scheduled for today. So if the alarm does sound, please calmly leave the building via the nearest fire exit, signposted and as directed by the designated fire marshals. Do not use the lift. And the assembly point is the car park at the rear of the building. Okay, so, and a further aspect is, if you are a user, and I guess most people are, a user of social media, it's hashtag GRIPS2024, with GRIPS lowercase, all one word. So, there we go. So, 2, new business models and behavioural change. I think this is going to be a really fascinating session because it calls upon so many disciplines that are actually outside the range of plastics technology. We need whole systems approaches to resolve some of the issues. But one can question whether that's too theoretical an aspiration. We heard this morning from Rachel's keynote presentation that public participation is required on a large scale, but that there are limits to the willingness of people to participate. For example, in the segregation of waste, in refill or reuse systems. And it involves psychological testing of self-discipline and responses to legislation, and education as well has a big role to play. You know, we're entering a world of material traceability, of product passports, ever-tightening legislation and associated penalties. And this encourages fraud and misrepresentation. I mean, one aspect also not covered by today's agenda is the role of productivity in manufacturing plants. It's all about the more efficient use of materials and energy, starting with design. It's all a very huge subject, so I think we'll jump into the first presentation, which is Dr. Peter Cook of Innovate UK. Would you kindly come to the forum?
Thank you, Philip, for that nice introduction. So my name is Dr. Peter Clark from Innovate UK Business Connect. Nice to be here today. And it's a real pleasure because I'm here to launch the sustainable carbon ambition for the UK chemicals industry. Hopefully this will be a really nice segue between the presentations you heard earlier and the presentations you're going to hear later. The report that stands behind this study that I'm going to talk about today is 160 pages long. I don't have time to go through all of that today. Philip's told me to keep it to as close to 10 minutes as possible. So I'm only going to give you a few highlights. If you want to learn more, please have a look at downloading the report. But what I want to do is share with you at high level some of the findings, as I think it's going to be useful for the discussion we're going to have on new business models and behaviour change. Okay, so first of all, I think I'm preaching to a room that pretty much knows this already, but let's just have a step back and think about how important chemicals are to our everyday life. We're touching them every single day in our home, in our garden, in the cars we drive. We can't get away from them. They're absolutely integral to our lives and to a modern and resilient economy. They're in 96% of all manufactured products, and in the UK we do have a thriving UK chemical sector. It's supporting 151,000 jobs directly and around 500,000 further jobs further downstream. When we have a look at the makeup of the chemical sector in the UK, we can think about it in terms of these subsectors, and I thought this group in particular would be keen to know where polymers features. So polymers represents about 20% of the revenue, GVA, and a little bit less of that are employment of the total chemical sector. And yeah, the chemical sector is really unique, isn't it, when we think about the transition to net zero. It's a unique sector because it requires fossil carbon, not just for energy, but also because it uses fossil carbon as a feedstock. And it's a complex sector. So this sector has been able to enjoy having access to low-cost, readily available feedstocks for the last 70 years. So particularly and that's given us economies of scale. Look at what's happening in China, in the US with shale gas revolution over there, elsewhere in Europe. We can see that we've really enjoyed access to coal, crude oil, and natural gas, and from that, we've been able to get all of these building block molecules, which you'll see in blue here. And then from that, we go through further steps, and further steps, until you eventually get to a product that we interact with every day. So it's a complex sector. But that's one of the reasons that we wanted to look at supporting the chemical sector. As we were asking these questions that I'm going to flash up on the screen, we started to think about what does the chemical sector look like in 2050 then, if we're recognizing that it needs to also divorce itself from virgin fossil carbon for energy, but also for feedstock. What does it look like in 2050? How is it going to get there? And when we started asking these questions that are on the screen at Innovate UK, we couldn't answer them completely, which is why we commissioned this study, which is what I'm here to tell you about today. So it started in September 2023. It was commissioned and undertaken by the consultants up here, so Frey Consulting Group, NNFCC and Perspective Economics. And I'm just going to share with you some of the high-level sort of thoughts and insights and findings from that study. So let's think about how we make chemicals, right? The way that we've broken it down is there are really only 4 options to produce organic chemicals. So that's chemicals based on carbon. There's only 4. Virgin fossil carbon. Today, 90% of all chemicals are derived from virgin fossil carbon. And really, our only other options are a biomass, of which there are lots of different forms of biomass. And then there's recycled carbon. We've talked a lot about recycled carbon already today. That might be recycled of plastic materials. So that's virgin fossil that's already in the supply chain that we're bringing back around. And then there's CO2, and that could be point source CO2, or that could be direct air capture CO2. But they are our 4 options available to us. And in the report, we talk a lot about the different factors that affect the availability of these different feedstocks. And life is never easy, is it? It's always complicated. And actually, we've already touched, I think, in the last sessions around some of the complications around the availability of waste plastic for chemical recycling, which I've highlighted in red there, in the red circle. Okay, so I wanted to just share with you some of the insights from the report. There's loads more in there, so go have a look at it. I now want to move on and share with you some of the stakeholder feedback. So we engaged with more than, I think, 250 individuals through this study, and I wanted to share with you what were the key findings. Here's a few of them. So 98% of those stakeholders believed that we do need to transition away from using virgin fossil resources. 100% of them said that it's not going to happen, you can forget about it, until there's no longer 100% of stakeholders agree that until fossil resources are no longer subsidized, this isn't going to happen. We're living in a dream. And as much as we focus on carbon and talk about carbon, this doesn't go anywhere unless we have low carbon hydrogen, and we need lots of it. And also, alongside that, we're going to need lots of renewable energy. A few other key pieces of feedback. There are significant gaps in the UK chemical supply chain. We still do have a very strong sector, but as I showed you earlier, it's complex. We do need to understand where the gaps are and where there's an opportunity to reshore and bridge some of those gaps. When we look to the future of what the future feedstocks might be, the survey said that ethylene and methanol were 2 key feedstocks to look at producing in a sustainable way in the future. And this is a really important aspect, this last one, and actually it came through in the earlier presentations. We're not very good at communicating always the value of what we do in the chemical sector and why this is an important aspect of the net zero transition that we should be engaging with. So we need to look at better communication with the consumer around this challenge. We also asked stakeholders what are the main challenges or barriers to accelerating growth, of which there are lots. If I just highlight the top 4 here, at the moment it's cost and profitability barriers, it's uncertainty around feedstock prices, there's regulatory barriers, and this last one as well, access to R&D funding at appropriate scale. And I think we heard that come through loud and clear in the last presentation as well. Okay, so that's taking all of that into consideration. We asked the consultants to engage with the stakeholder community and come up with a scenario. We wanted to ask them to tell us what the future might look like and get consensus, which is always hard to get. And the consensus is the ambition that we've set as a group of stakeholders is that by 2050, the UK chemicals industry will have doubled economic output, significantly lowered its greenhouse gas emissions, and it will be sourcing 80% of its carbon requirements from non-virgin sustainable carbon sources. And this is what the transition looks like. So this is what the stakeholders have agreed is the most likely ambitious scenario. So what they're saying is by 2050, we'll still probably have some virgin fossil carbon that we're having to use to produce chemicals in 2050, around 20%, but we'll need to be sourcing at least 20% of our chemicals from CO2, 30% from recycled carbon, and 30% from biomass. The consultants have also had a look at giving us some numbers. I think we struggle a lot with the scale of this challenge, And it is a meaty challenge, but we've started to get some numbers now around how much carbon are we going to need, which is really valuable to start having a debate around, well, what does that look like in the UK? How are we going to get that much carbon? And I think importantly, we're also starting to get a really good grasp on what are the interdependencies that will affect the trajectory of any one of those feedstocks. So for recycled carbon, it's how do we get those recycling rates up? For CO2, how are we going to actually capture all of that carbon from the point sources? Where are we going to get our renewable energy from? So what needs to change to make that happen? We said there's 4 key things. This is a transition, it's a journey, it's not going to happen overnight. We're not going to be switching off our refining assets anytime soon and just switching them off and onto all of these other new feedstock pathways. We need to take care of the assets we have here today, look at how we can help them transition, look at electrification as an option. But then 2, 3, and 4 are about bringing on the new feedstock pathways. Biomass has some great opportunities, chemical recycling, and also CCU, carbon capture and utilization. We need to be investing in all 3 of these technology pathways. But they're all going to be enabled by better understanding about where our feedstocks are, how truly sustainable are they, talk a lot about life cycle assessment, policy. In the report, we talk a lot about needing best available carbon management. At the moment, we have policies that are dictating where some of these carbon feedstocks go, and they're not necessarily looking holistically at what would be the best use of that carbon. Thirdly, we need collaboration and investment. So take-home messages from today. There's a once-in-a-generation opportunity to invest, but we've got to invest pretty soon, now. If we're going to help the chemical sector transition, as we need to transition to a net zero and circular economy, but there is that opportunity to do that now. It's a journey. There is no single alternative to virgin fossil carbon. There just isn't. So we need to be investing in all 3 of these areas, not just one of them. And we need a more joined-up approach to managing carbon, looking at the best use of it across chemicals, fuels, materials, and energy. But ultimately, and I think this plays into the discussion we'll have, I don't think any of this is really going to happen unless we have changes in consumer behaviour and changes in business models. So thank you very much. I'd just like to acknowledge all of the people that have been part of this report. The study builds on a lot of great work that's been done by other actors in the innovation ecosystem as well. If you did contribute to the report, thank you as well for your contribution. Thanks.
Thank you, Peter. What we're going to do, I'm going to ask you to save your questions to the end of the presentation, and hopefully we'll have a good slab of time there to generate a discussion. So if I can call John Ferguson to the podium at Bin Eco Park.
Thank you very much, Philip. Thank you very much, Peter. Great presentation. That is just such a missing piece of a jigsaw, actually, to get value from other areas of plastics that are just not valued at the moment. Communities of interest are always so interesting. You know, you're in a room speaking. I know every single one of you here today because you're really interested in this topic. I'll try and stick to time, 10 minutes, to tell you something about a system change. Before I do that, and I won't dwell on this, but my background is 36 years as an environmentalist. I worked with the Scottish Environment Protection Agency within Scottish Government. 12 years ago, I left, retired into kind of my own business as an industrial ecologist. I'm fascinated by low-carbon transitional use of technology into regenerative economies. And I've been working in plastics for about 10 years to try and understand what is fundamentally broken. And there are many things broken about plastics. But I'm going to try and show you one thing that I think we could do that would be one aspect of a multi-stranded approach, a multifaceted approach to dealing with the complex impacts of a material that is essential to modern civilization. It's not plastic's fault that we're in this situation. It's our fault that we're in this situation with plastics. So I'm going to tell you today, so I'm head of strategy at the Bin Eco Park. I also have a couple of my own companies that I do separate projects, and this project is one of those projects, and that's Polymer, as you'll see there. In terms of, the problems I see with plastics, I think we're highly selective. We go, we want this, we want this, we want that, we'll have that. Well, we don't want any of that. So the minute you don't want this, that plastic goes into the mixed residual waste stream. There's only two things can happen to that waste stream. And that's if it gets there at all, by the way, because quite often it doesn't even get there. It's just litter. And that's a whole other story. If it gets into the residual waste stream, it goes to landfill or it goes to incineration. And we've heard today in some of the talks, I'm not sure if you were there, that landfill is better than incineration. Well, only marginally. Landfill is the worst place for anything, by and large, because actually you've mixed it all up. It's very difficult to get it back. And macroplastics in a landfill will become microplastics in due course, point one. And an incinerator, we're basically saying, here you go, have the carbon, at a time when we need to reduce carbon. So we don't want to be burning plastics. The challenge there is we've built the incinerator fleet to operate within a fixed engineering scope, called a firing diagram, and you can't take all the plastic out, or they don't work. So we've got ourselves into a bit of a conundrum here, where we need to better understand the plastics we can take out. My view is take all the plastics out and give the incinerators back the worst, lowest grade plastic that they must have to operate, and then gradually try and move out of that generation of incinerators that don't need plastic. Okay, so massive leakage of plastics to residual waste, that's about 80%, 85% globally. That's the bit I'm interested in the moment. It's a very fragmented supply chain for recycling. There's few demand-side drivers for recycling. Those of you involved in recycling, this has been a debate for years, is trying to coordinate supply and demand. Where are, other than perhaps in some elements of packaging directive, where's the demand-side drivers to say, you make this product, you've got to use recycled plastic? 50% for that product, 30% for that product. Medical products probably exempt, no recycle is needed in some cases. And in some cases, 100%. You want to make that 100% recycled plastic. That starts to drive demand. And the people that stop that, well, I won't accuse anybody of stopping that, but there are sectors that don't like that idea very much. There's a massive undercapacity of indigenous infrastructure, and marine plastic pollution is demanding novel systemic solutions, because we know that that is an incrementally increasing problem, because we're doing nothing about stopping that leakage into the oceans, and it will catch us if we don't do something about it. Okay, so the problem that I see is 80% of plastics treated in mixed residual waste systems, leading to massive wastage of a resource and high non-biogenic carbon impacts, largely through incineration, because that's where most plastics will go. We are moving globally away from landfill towards incineration for residual waste management. The solution is to treat all post-consumer plastic waste as the complex group of materials they actually are, by moving plastic out of mixed waste into integrated residual plastic treatment systems with added value valorization options and safe material conservation storage, called land banking. And it looks a little bit like this. You can see there that all residual waste, from commercial, industrial, that's construction, demolition, it's agricultural, it's municipal, it's trade waste, any type of residual plastic that would go to residual waste, should be moved out of that residual waste so it's not mixed with the other materials to create its own residual waste stream. That should be signaled through price signals. Those price signals will come from the fact that incineration in 2028 comes into the emission trading scheme, and on top of your, by then, 130, 140 pounds a tonne gate prices for your incineration feedstock, you'll have another 50 to 100 pounds a tonne to pay your emission trading scheme costs. There's a strong price signal to play with, to say, if you separate your plastic from your residual waste, your waste charges will plummet. Then we get these plastics into this system I'm about to describe, and we start to remine that material for the good quality polymer for mechanical purposes. We identify the small films as the feedstock for the depolymerization sector. They can deploy a whole range of different technologies. Their struggle is getting hold of the feedstock. You ask them what they want, they will tell you what they want. I want polyolefins, I want polystyrenes, whatever. I will say, where's your plastic? They will say, well, you've got our plastic. I said, no, your plastic is in 1 million bins. How do you get your feedstock out of 1 million bins unless we do something that changes the fate and the route for that plastic? It takes marine plastics, so commercial, industrial, domestic, and marine plastics. It strips out the best quality mechanical. It creates the feedstocks, largely small film for feedstock chemical recycling. We have a clever system called polymer fusion molding, which is not extrusion, it's an intrusion system. It's very flexible in the kinds of building products that it can make. It can make reinforced ballistic materials, it can make fiber reinforced, metal reinforced, it can label, exterior coat, it can create thicknesses up to 40, 50 mil, very thin sheets if you want thin sheets. Very flexible, and it hoovers up the microplastics that you get recovered from your washing systems. I published a paper in the Institute of Materials Mining and Metallurgy this year in March about the challenge that we need to do better in recycling. The minute we do better in recycling, we've created the perfect engine for microplastics. So we have to have policies that go, we've got to recover the microplastics, that's going to cost money. If you can use the microplastics and give them a value through things like polymer fusion molding, then you've created a virtual connection that supports improved material and nanoplastics recovery, because we don't recover much below 200, 300 microns, maybe 100 microns. Everything under that is gone into the wash system, into the sewage treatment works, into the oceans. So recycling has got to increase, but not at the expense of the microplastics. And then you're going to have an overburden of materials. So the conversation there is land banking. We're in discussion with SEPA. Could we land bank this material, dry sell it, inventory it, geolocate it, and make it accessible for the future? It says it's safer there than in a landfill because it's a dry system. It won't break down over time and create microplastics. And it is easily recoverable. You try and recover plastics from a landfill site. Dirty, dirty business. You lift the lid on the land bank and there's 40, 50,000, 100,000 tons of plastics in the future. And if it has to stay there for a long time, it's safe. These are transferable systems. They can go anywhere in the world. And it targets all residual sources, specialized sorting of large and small films and ridges, polymer selection by quality, so you're looking for the best quality material to take out from mechanical, small films to chemical feedstock recycling, micro and nanoplastics, deeper recovery because you can value that material instead of creating extra cost necessarily, onboard washing and granulation, even pelletizing, land banking of excess material. Each center has an R&D focus and involves treatment. It can test new systems. There's such an evolution in the technologies in this space. Training and education. They can be networked. So if you have a network, they're decentralized. They work within catchments. The plastics doesn't have to travel too far. You might have one specializing in manufacturing. You might have one specializing in depolymerization and so on. And they're transferable. They can go anywhere in the world. They can create small microplastic economies on islands, wherever you put these things. Okay, so instead of plastics being a problem that you just throw away and it ends up in the oceans, you create a plastic economy by changing how you manage residual waste plastics. Okay, last slide. So in terms of delivering the project, I have 5.2 million awarded to me in a Tay-City deal. City deals all over the country. I applied for this. I was one of the architects of what the Tay-Cities deal looked like in terms of the scope of focus. And I managed to get circular economy in there. They rewarded me, invited me to make a bid, one of the few private sector companies that got some money. It's optimal for commercial, industrial, and domestic. But in the first instance, I'm focusing on domestic waste because the emission trading scheme is going to hammer local authorities. And I want to offer them a route out of that added cost. The EPC, engineer, procure, construct, and the operate and maintenance are complex and need solutions. It's perfect for build, own, and operate. But I'm looking for the right kinds of partnerships. If it's funding based on contracted feedstocks, you'll get material coming in with a gate price because you've got a lot of offset costs that you're saving, so it's a large margin to play with gate price value. Land banking regulators under discussion with SEPA. It requires a high level of public, private, and policy integration. Exclamation mark, exclamation mark. I bridge both sectors. I've worked in deep policy and strategy. I work in the private sector. It's challenging. It's the biggest challenge is to get everybody working together to strategically deliver this kind of solution. So any help is welcomed. Systemic change is really easy. And my prayer today would be, if there are smart and wise people in the audience that feel they could help with this, I'll show you my contact details. Please take my contact details, get in touch with me, because I'm a tiny company. We know what we're trying to do here, but the leveraging, the scale to deliver this first facility is really pressuring me, and any help that you could offer. And if you know people who would be interested that are not here today, please do pass on my details, and there's my details, my mobile phone and my email, and I'd be delighted to take this conversation up with any of you. Thank you very much for listening, ladies and gentlemen.
Thank you very much, John. If we can now move on to Anne Stevenson, Resource Futures. Thank you, Anne.
I need my glasses. I can't see my notes without them. Sorry. Can everybody hear me? Excellent. Okay, so let me just check. Oh, no, wrong way. Resource Futures. You've probably never heard of us, but we're an employee-owned, independent environmental consultancy B Corp, and for 30 years we've been helping organisations address a multitude of challenges related to waste and resources, which is why I'm here today. I'm the Circular Economy Lead at Resource Futures, so I'm there to try and help organisations help take their part in that transition to a circular future. Obviously, plastics are an amazing material, but we have to change the way that we use plastics and what and how we recycle for a more sustainable world. The thing is, we can't, and there's been lots and lots of talks today, and there will continue to be, we cannot rely on recycling ourselves out of the problems of wasting plastics, as many of the recycling processes do remain energy intensive, might not produce the required quality of recyclate that we need, and remain often an out of sight, out of mind solution to linear models of production and consumption. So I'm here to argue the case that if we are serious about transitioning to a circular economy and addressing climate change, we need to put in place a range of business models that go beyond recycling. Now, there is a pathway to at least making European production of polymers and resins net zero by 2050. And as outlined by Peter, this relies not only on decarbonising production, but that will only reduce emissions by 45%, by the way, but the ability to promote the reuse of plastics, to adopt circular business models that improve materials utilisation, and increasing the use of circular feedstocks, as we've discussed about using CO2, and displacing those fossil-based feedstocks, lowering the demand for virgin fossil-based feedstocks. So what I want to focus on is that vision for a circular future for plastics that not only addresses the problems of our growing reliance on imports of plastics that have significant implications for sustainability here in the UK and in the systems overall, but the problems of exporting waste and the issues of plastic leakage. But the problem is where do we actually start? We need to rethink the way we make, use and reuse plastics. Essentially, we've got to redesign the system in which the material is used, which all sounds nice and theoretical, and I know what people are thinking. But what this means in practice is actually starting at the beginning and at the top of the waste hierarchy. We've got to eliminate the problematic or unnecessary plastic, and this is through three key steps: the redesign, innovation, and new delivery models. And yes, the majority of the time, the focus is on plastic packaging, but it's not surprising given that 40% of total plastic production is for packaging, and 70% of the UK's overall plastic waste is packaging. But irrespective of application, we do need to start adopting green polymer chemistry-based business models so that all plastic-based products are sustainably produced and are 100% reusable, recyclable, or compostable in practice and, importantly, at scale, and especially for packaging. But this has all got to come without us affecting the functionality of those materials. We've got to adopt design-based models, so we actually use less virgin material, and we do have to increase the uptake of reuse models. So when talking about green polymer chemistry, here I'm not just talking about producing greener polymers. We've heard some of that if you've been on some of the earlier talks today that have reduced toxicity and ability to be reused and recycled, but greener polymer production processes and greener recycling of polymers after use. But if you didn't sort of attend the earlier sessions when we're talking about green polymer chemistry in terms of greener polymers in production, there's a couple of papers here that I find really, really useful. So I would recommend you go and look at them. But as this session is about business models and behaviour change, I'm going to focus on the challenges of cognitive biases when it comes to polymer production chemistry and plastics recycling. Now, I came across this when I was developing the Circular Economy for Chemical Engineers course for the IChemE, and it related to work of an organisation called Syngenta, who were looking at their use of solvents in the chemical synthesis of their products. We know that solvents are an everyday chemical and are inherent in the production of polymers and polymer recycling processes. And although that was on solvent use, we're well aware that polymers have a vast array of other chemicals and additives, with earlier talks about additives in polymers, and many of those are classed as chemicals of concern, which is why I wanted to highlight these three biases that were found at play for Syngenta, but could equally apply in polymer production and polymer recycling processes. And in effect, all of them are in relation to sort of forces of habit. We don't question the way that we do things. So the first is the status quo bias, and it's always been done that way. It's the lack of incentive or a lack of convincing reasons to change from more sustainable chemical, additive or solvent. Then there's a belief bias, which is that a particular solvent or chemical or additive is the only suitable option for their reaction, and there's no truly other alternative available. And then there's the precedence bias, and we're in a university, and this will probably be one of the main things that will be affecting the way that we design future polymers, is the literature or existing operations that use the chemical or solvent or the additive you're currently using or planning to use. They never report any other alternative. It is just that's what you use. So by recognising these sort of biases are at play, Syngenta have worked to initiate a mindset change. So this is about changing those practices of chemists, chemical engineers, any sort of engineering in production. And so they changed it, and what they ended up doing was reducing their hazardous solve reduction by 75% in 2 years. And a key message I want to get across here is that they didn't just focus on the large-scale operations, it was the small-scale operations. So the reason they addressed the small-scale operations was that small-scale chemistry often ends up to medium and large-scale as is. So even at sort of concept and bench scale, it's important to think green chemistry first so you don't become locked in later. And so when we talk about design-based models, as already mentioned, packaging is a key issue and lots of challenges around that. And yes, there are brands and retail signatories to the Plastics Global Commitment have doubled the use of PCR, post-consumer recycled content in their plastic packaging over 4 years. But the Ellen MacArthur Foundation has given a range of examples of the really good stuff that's happening in this thing, but they've already shown that signatories are unlikely to meet the targets, and there's still a long, long way to actually go. And this is because the global market, we're operating in this global environment, and the global market continues to increase the use of virgin plastic and grow the production of problematic packaging out there. So what I thought I'd cover under recycled content and design-based models is chemical recycling outputs as recycled content. And I'm not an expert on chemical recycling, and you may have already been to the chemical recycling talk there. And of course, there is a BPF seminar on the 17th of October, which you could attend to, which goes into detail. But I just want to highlight that when we talk about chemical recycling, it is a broad spectrum. And what's really, really important is that it's to work in tandem with mechanical recycling. We're not talking about something that is going to overtake it, okay? It's there to deal with those really problematic plastics that are currently in use. And so this is just an example that you might be interested in about the use of outputs from chemical recycling facilities. Now, BASF have been doing this for a number of years. They've now got 200 mass balance certified C-cycle products. Not all of them are packaging. And if you go through and look at their LCA meta study, and you'll find that they would expect that in most cases, it's supposedly more environmentally better than the other systems that are there at the moment. But from an environmental point of view, mechanical recycling still does tend to outperform chemical and solvent-based recycling, the ones that are currently in practice when we're talking about pyrolysis and things like that. But what we'll say is if you are interested in LCAs, there's this paper which you might be interested in which compares them. But also with chemical recycling, it's not just the environmental sustainability that is an issue, that there are still operational limitations of those technologies. And the next generation technologies that are there are still not at commercial scale. But obviously, I'm looking forward to when we actually get in the Mura Technologies plant, hydro PRT plant on Seaside, see if that makes much difference in terms of the environmental credentials of chemical recycling. Now, finally, reuse models. There's significant challenges from moving from niche to scale. And some of these models we are very, very familiar with, like refill. We've got about 200 independent refill shops around the UK at the moment. And the problem that we've got is moving from niche to scale. And while lots of companies have launched refill and packaging reuse pilots, and we have a number of lifestyle refill on-the-go stores around the UK, reusable packaging is still stuck at 2%, and it's been there a long, long time. Okay, so there's still major challenges to overcome, and that's combining the practices and behaviours of producers and users of products and infrastructure issues. And they're really closely interlinked, because if we can't support the infrastructure at a cost that makes the options still acceptable to end users, and if end users are constantly wanting lower costs and ultimate convenience, there's insufficient margin to invest in reuse models, and we'll continue to stagnate and have major problems in this area. So due to these various factors, one of the key things that we've got to accept with reuse is it's got to meet or exceed the sustainability break-even point. And what that means is that you have to achieve a 90% return rate of plastic packaging for reusable plastic packaging, which is going to be a major challenge in terms of behaviours. And so the main thing is, though, that for them to actually work and have the desired positive effect, a systems perspective has to be adopted. And this is, as John just mentioned, he brought up the concept of the systems perspective. And this applies not only to the reuse models, but recognising that circular economy practices are influenced by a range of external influences as part of that wider ecosystem is essential. And this is from some research that I did on the prevalence or otherwise of circular economy practices in businesses in Scotland. And so these are the sort of these number of ecosystem elements that have to be supporting each other for real change to be happening. And so as we go up the elements, so from the bottom to the top, they're easy to influence in the short term, but the impact of any intervention is likely to be low and struggle to take hold if we haven't addressed the fundamental ecosystem elements at the bottom. So I just want to close on this theme of this session. For the success of these business models and that supports the circular plastic revolution, we need to first address the prevailing measures of value within the UK or within the global plastics system, and that's the economic-centric, which generally means low cost, convenience culture, and that adopted in decision-making throughout. And then we need to, have we got another slide? Yep. There we are. And then we need to address the embedded cultural attitude to plastics, the environmental and the attitudes to the environmental and sustainable products that are out there as well. So, people have perceptions of hygiene issues, that sustainable products are seen as lower quality and failing earlier than traditional virgin products. And as we touched on when looking at green polymer chemistry, we need to address the knowledge biases and forces of habit that are influencing the production of polymers and how we currently think about recycling of plastic polymers. So I hope that was interesting, and I'll hand you back. So thank you for listening.
Okay, very good. We'll move on, and then we'll take questions. May I introduce David Landsberg of Peasy.
Thank you. Good afternoon, everybody. My name's David Landsberg from a company called Peasy. It's wonderful to be amongst such distinguished speakers from which we can learn so much. Let me assure you, you're going to learn nothing from me. What I'm going to show you is common sense that you already have anyway, and you'll know everything I'm going to be talking through. So the first thing, obviously, is it's only waste if it's put in the wrong area. And what we do is we make sure that people put it in the right area. So there's a lot of bins. I don't know if anyone wants to have a guess, but there's between 80 and 120 million bins in the UK. They cover just about every waste stream. They're just about everywhere. So it's perfect for a true circular economy. You put the right thing in the bin, it ends up in the right place. It's reused, recycled, whatever. So that's a great infrastructure to have. Unfortunately, it relies on one central premise, and that's that we put the right waste in the right bin. And that's where it's falling down. We've made it very confusing. It takes a lot of effort, and it is failing. According to RECOUP, 84% of people are putting the wrong waste in the wrong bin, mainly through confusion, often through wish cycling. So we know we've tried finger wagging, fines don't work. The evidence shows that. And the consequence of putting the wrong waste in the wrong bin is obviously not as serious as driving a few miles over the speed limit. And we all do that, don't we? Or was that just me? Just me? Okay, let's move on from that. So this is where the fun starts. What we do is we make people put the right waste in the right bin because it's fun, it's engaging, it's rewarding, and secretly we're educating them too. So our QR code goes on any poster, any signage, on any bin, any waste stream. It doesn't matter, as long as it's got the relevant QR code which we configure for that particular site. We configure it to give our weekly jackpot, which everybody plugs into. Our weekly jackpot is £1,000, by the way, and instant prizes as well that may be relevant for that specific site. So just scanning the QR code opens up this screen that you can see. You just put whatever it is you want to dispose of in front of your phone. You don't need to scan any barcodes on the product or anything. It recognises absolutely everything, and I do mean absolutely everything. It surprises us, but I'm going to ask you to experiment with it in a short while so you can play with it yourself. And if you're standing in front of several bins, it will tell you which bin to put your waste in. And if you're standing in front of one bin, it will know that too, and it will tell you whether what you're holding is relevant for that bin or not. And because we give away this jackpot every week, and there's instant prizes to be won, people want to get it right, and it takes just a few seconds to do, so they want to do it again. And the more you do it, the more entries there are into the prize draw. So the question I get asked all the time is, yeah, but what about people that cheat, that try and game the system? Which is a fair question. And of course, our AI measures a lot more than just whether or not the right waste is for the right bin. We've got a lot more behind that. We've got 7 different levels of fraud detection. But actually, we welcome people trying to game the system. And the reason for that is the people, and it's only a small percentage of people, but the people that try and game the system are exactly the people whose behaviour we want to change the most. So we let them think they can game the system. They can't, by the way, win a jackpot because the jackpot is checked by humans and everything's completely verified and all of their previous entries are verified. So they can't win the jackpot. But they do try and game it, and they try and take pictures of the most obscure and bizarre things. I don't know if you can read that. Can you see it from there? This is a dog someone's taken a picture of, and our AI has said this image contains a dog which is not a recyclable item. That's for future reference. So we know it works. We have a sister app. This system, by the way, I'm talking about doesn't require an app. It's just a QR code. But we have a sister app called Litterlotto. Litterlotto incentivizes people just to put litter in the bin. We use the same nudge technology, the same incentivization. We're up to about 24 million pieces of litter that have been put through the bins through our app. So we know it works. The first results have come through on our first trial with the Bin It to Win It QR codes. And the first facility we tried it with had a contamination rate of about 40%, which is actually not too bad. But we've managed to, the results show we've managed to get that to below 4% contamination. So it's working. People are changing behaviour. The next problem, though, is when we ask people how much contamination do you have in your bins, no one seems to know. They all seem to think they've got a lot of contamination, but no one is really sure of it. So we've created a tool which we call our instant bin audit, and just taking a picture top down of any bin, it will give you an instant report on what level, what percentage of contamination is in the bin, and it will also tell you what the offending items are. So this can also be configured for any type of bin. So now we can actually report on people's waste contamination in their existing bins, and then we can show them how to improve it. That's the QR code if you want to have a go with trialling that, just to see. You can put anything in front of it, and I think you'll be impressed with the results. Try it, tax it. This is a demonstration of a installation we've got in Lloyd's of London, in the city. They've got 7 apertures in one bin. So the results, that when you scan something using this QR code, it will tell you which colour of those apertures to put it in. So it won't mean much to you in the real world. It's specific to that location. The smaller QR code is my LinkedIn profile, if you'd like to link with me. Thank you very much.
Can I ask the speakers to join me across there in the... we'll take the questions there. Which one do you think?
One for the speaker, for the questions.
Yeah.
We'll get to coach up.
We do. I'll see. Okay. Can we take questions, please? Any questions? Gentleman at the back there.
Hi, I've just written mine down, so this one's directed to Peter, and you mentioned biomass as a vital alternative feedstock for polymer production. Have you calculated the land use requirements to produce this, and can it be sustainably delivered with other growing and competing land demands, food, energy production, and so on, and the need for biodiversity protection?
Did you hear that as well? I think can you really speak up and we'll try and shout out the...
Right, I'll try again then. Okay, this one's for Peter.
Good.
You mentioned biomass as a vital alternative feedstock for polymers. Have you calculated the land use requirements to produce this, and can that be sustainably delivered against the other growing and competing demands for land, for food, and energy production and biodiversity protection?
Thanks. Yeah, great question. I'm struggling to remember the details that are in that 160-page report, but we do look at, realistically how much biomass we think we can get. But it's absolutely, we talk about the interdependencies, and for biomass, we need changes to agricultural practices. We need to look at the competing demands. So, as with all of these feedstocks, when you look at them, they've all got these different interdependencies and challenges. But that is looked at in the report. I just can't remember any of the numbers off the top of my head.
I just want to add, though, I don't know if you went to the talks earlier on where the examples of Braskem and somebody, I can't remember the names of the organisations, but they're using the waste products from food production as their biomass source. So I think, again, it's thinking differently. Why are we growing something specifically when we've got lots of free stuff near enough from food production processes already that could be part of our solution? So that industrial symbiosis way of thinking as a circular business model is where I think personally we need to look at first, rather than thinking of growing something new.
That's my son's name. Sort of building on this theme, we look at secondary products from food production, but I was talking to somebody recently, and that material is just ploughed back into the soil, but that's contributing to soil health. And it's estimated in the UK we have 40 fertile harvests of soil left because of the poor, the reducing quality of our soil health and its loss. But it's not just plastics, is it? There's 60 to 70,000 other chemistries that we're looking to get, we get from oil. And I really don't feel that the impact on our planetary boundaries of shifting to biomass has been properly addressed. Is there any intent to do a deeper dive into that?
I think what comes up quite strongly is needing to do better life cycle analysis for all of these different feedstock types. I know there was a biomass strategy launched by DESNES, and I know there was a small mention of chemicals, and I know there's plans to do further studies around the viability of that, but I'm not sure how far they're going to go in relation to dealing with exactly what you're talking about. But yeah, it's challenging. But I don't know how we're going to. I don't know exactly which study is going to give us the magic answer for that. I don't know if anyone else has any insights.
It's been a question for 30 years. How many issues do we take good quality agricultural land out of production for food? We can't do that.
Sorry, I was just saying, it's been a question for a long time. And for me, the issue is what do we use the land for? So if you can use secondary biomasses for niche markets for biopolymers, fine, but you can never weigh anywhere close to the transition volume-wise without taking massive amounts of land into the production of biomass for polymers, which risks global food production. That's my opinion.
There is also an argument, though, that a lot of land that could potentially be used for food production is being taken out of food production to produce fuel for us to be able to continue doing our flying and driving and things like that. So again, it's this, but that's what I mean. So, but that's the thing. So what if that was towards polymers and materials that we need, and we had alternative ways of generating energy? So it's just complex, and I think it's one of these things that these are the discussions we all need to be having, and we need to challenge each other and our way of thinking of, again, coming back to the biases. Unless we actually just fundamentally question, well, why are they saying that and how does that happen, we're not going to move any further forward. So I would recommend everybody to just have their little critical eye on everything that they read and think, is there an alternative?
It suggests that it's a good call for UKRI to put a call out for funding for looking much more closely into this area.
Yeah, and I think when we talk to a number of leading academics that are looking at this from a system-wide perspective of what we do, there are groups looking at this. I think we need more joined-up funding looking at this sort of challenge. That's come through pretty clearly.
I want to ask you a question.
Oh no.
John, you said in your presentation that one of the factors that would encourage, a positive growth of, a sustainable chemical industry in the UK is more joined-up thinking. Now, you just used an expression, joined-up funding. How do we get in this country, applied to the chemical sector, joined-up thinking? Sorry.
Thanks. I mean, I think there are lots of groups, a number of whom are in this room today, who are really trying to come together with one voice around what's needed for the chemical sector because it's so diverse. It's look at the sectors that have got huge amounts of funding. They're automotive, aerospace. It's much easier to wrap your head around what a car is and why I need it, rather than the chemical sector. So we need to see the chemical industry, I think, coming together under one voice. That's why we did this report, to try and get an understanding of what the industry as a whole wants. Then it comes to funding. We hear it a lot. It's mentioned in the report. And there's data in the report around investments that we're seeing around the globe. The UK isn't securing as many investments. I think there's a stat in the report around UK chemical companies receiving 14 times less investment than, say, companies in Germany and the Netherlands. So how are we getting all the way through that innovation cycle from early stage innovation through to commercialization? Someone mentioned it before, didn't they, around how complex the funding system is. We've got loads of great assets here and a great system. But yeah, I mean, I'd love to see in the future a joined up low TRL through to high TRL deployment type funding system. There's lots of people in the background looking at this. Dare I say it, what I hear from industry, and again, it's in the report, is, we'll probably need some form of industrial strategy to start driving that. And from there, you can start to look at, well, what sort of long-term investment do you need? But in the chemical sector, it does need to be long-term, doesn't it? How long does it take to just build a chemical plant once you've made the decision, let alone to do the development bit before then? There's some great examples of where we've done good stuff. I think you mentioned, Mura, recent investment by Innovate UK in a demonstration scale plant. That's just one plant. I think we can also look to the aviation industry. I think the aviation sector is actually going through the same transition that we have. And look as well at what you've got to look at there is the way that they've managed to, there's been co-investment in development and deployment, but at the same time, there is policy development as well. We now have a mandate that the government is looking at that's saying, I should know what the mandate is, someone else in the room might know, X percentage of SAF by 2030. Those sorts of things, those mandates by government will help drive investment, will help join up the innovation pipeline. I think I've prattled on enough there. So,
can I offer an observation on that same question, though? And it's in Scotland, we're starting to develop the concept of landing strips, which is bringing together all the components that deliver a project. So any project, it can be a new circular economy business to manage plastic board or plastics, or it could be the sustainable fuels for the aero sector. How do you strategize the delivery of that infrastructure? How do you operationalize that policy? Because over 36 years, it gets tiring watching the conversations going round and round and round. All good, all relevant, all doing things that are necessary, but not delivering. And in Scotland, at least, and I won't comment on England, we don't deliver on policy. We're really good at good policy, but we don't deliver it. We're always chasing our tails, monitoring how we're doing, and I just go, stop chasing your tails, monitoring how you're doing, and deliver something. Understand the pipeline. So we bring the development agencies, the funders, the planners, the consultants that can do land searches, the regulators, into teams and say, this project needs the following. And they've all, we're developing a memorandum of agreement, we're developing a funding ecosystem. We can bring and mobilize activity to deliver projects much quicker. And it's just asking the question, how do we operationalize the policy? Because we've lost the gift in Britain of doing that. And we're running out of time. We really are running out of time. We've got to change the system by building things.
Okay, thank you. Any other questions from, sir?
Can I be heard? Donaldson, Horner's company. A number of questions have been posed by the panel, yet they've answered some of them themselves in the presentation. First thing is state of mind of all of us, where we've grown up with a mentality that plastics are waste, and that has to be changed dramatically. And that, to some extent, is a lot of bodies need to change. The question of government in their involvement in all of this is actually quite major. Where in Rachel Reeves' summaries of her economic disaster that she's inherited, has she mentioned things like recycling and polymers and things like that? Not a mention, and there are a number of reasons for that. We are economically conservative as a nation. Our investment priorities are often obscure and always delayed. Secondly, we are served by silo government. And therefore, no ministry has complete responsibility for nearly all of the things that we've been talking about during today. We talked about as well of the ignorance of our administrators in government. This is a huge criticism of government, especially our MPs. How many MPs now in Parliament have a scientific basis or a basic in logical thinking? I bet there are very, very few now. I think there were only 5 in the last Parliament. We have also a treasury which is actually dominated by a restrictive. They should be called the nowbery rather than the treasury. What has been mentioned today indirectly is one of the ways in which we can move forward, and it's been used by using economic instruments. It was mentioned by John indirectly. It was mentioned by David certainly at the end with his incentives and his. But the incentive there we were talking about incentives, but rarely, in fact, the downside, which in fact are the penalties of failure. And so unless we get a market that works in that way, we are not going to succeed in changing minds. Until it affects people's pockets, they're going to be reluctant to follow the lines we should follow. So we need a set of economic instruments. I did a paper for the chemical industry 30 years ago, which says we have to get involved with government in setting up economic instruments. So therefore, we have to be in a situation where any incentives that people like Philip and others can actually push for in government, and not to delay and speeding up the processes, we're going to be following rather than leading. We have big problems in the way that we think in this country, and we have to change them. We have to build a society which is based upon cooperation and not competition. And that's where we basically are as an economy. We've been brought up that way. Now we are only going to succeed by mixing public and private resources. And departments and again, that means breaking up government silos and getting some better cross-government thinking. So a lot of the questions you have answered yourselves in your presentations, but there are some big hurdles out there as well. One of them being a government that thinks that you can change the laws of thermodynamics in a court of law. And also who believe that it doesn't matter, we can delay environmental measures without realizing that every ton of carbon dioxide we make while they delay stays up there, doesn't come down again. Thank you for listening.
Has anybody got a response to that?
I had a question.
question, but...
Yeah, go ahead. Please do. Yeah. We need to
Sorry. Thank you. Kelly Botham from Innovate UK Business Connect. I work in the Net Zero team. But personally, I have an interest in plastic sustainability. And so I love seeing this QR code that you have. I use Little Lotto personally, still waiting to win a jackpot though. So, but this question of recyclability, I find it frustrating as a consumer figuring out, you know, you had a lot of the challenges listed on your presentation, but it always seems like every presentation I hear people talk about is an issue with education and awareness, and I see it amongst my own personal family and friends. And I'm just wondering, whose job is it? It seems like it's just very itty-bitty. Whose job is it to raise the education and awareness so we know what we should be recycling and figure out how to integrate it into our environment so that we can make it easier for everyone, so that it just starts to happen naturally instead of, because right now it just feels so inconsistent. It's different from county to county, how we do things and things like that. And I'm just curious who and how. Should it be the government? Should we have some big campaign? But how do we make it more integrated and raise the education and awareness? Because there's so many people I know that's just still throw all the things that can be recycled into the rubbish bin, and drives me nuts. So.
Hi. Last week I presented on something very similar, but it was to do with aluminium foil, actually. So that was with AluPro. Similar sorts of issues in terms of complexity. And that's the thing with plastic, is no different to foil in terms of the complexity of packaging. And that's what causes this confusion in what we have to do with it. So I think it's a double-pronged approach. So it has to be led by something like simple as recycling. I went to Poland recently, and no matter, massive country, no matter where you went, it had 4 different colours, every public space, every Airbnb, every hotel, and it was just absolute consistency. So everybody just knows yellow means this, blue means that, just do it. So we need to have that consistency across all local authorities within that framework, but there is also an onus on packaging producers, particularly, to be really, really clear on the labelling and the packaging. You can't have something. One of the things I argued for last week was, you know, binary helps, but the one that says check locally, nobody's going to do that.
So I think first of all, behaviour change doesn't happen quickly. A lot of people think behaviour change happens in a couple of weeks. It can take years to change behaviour. But it's a bit like the broken window syndrome. If you see a broken window, it means nothing. You'll tend to find that there are loads of broken windows together. And it's also been proven that where there's a lot of litter, crime increases. It's about having respect for your area. And if we can reduce litter, for example, and people get used to seeing less litter, they will litter less. And it's the same with recycling at home. It will be a slow, gradual, I believe, a slow, gradual behaviour change where we hope to be kick-starting it with the incentives, because the carrot is always more responsive than the stick. And eventually it will become the norm. It's a bit like boiling a frog. When I was young, we had one bin that the dustman would take out for us. And, it seemed absurd when we were told we were going to have 2 bins and we had to put them out ourselves. And now look at us. We've now got, in Wales, 7 different waste streams, and that will become in a generation the norm, and people will be used to doing that and automatically segregate as they should.
So I agree with consistency. I agree with behaviour change and education. The system has to have the resilience to do the right thing, whether people behave right or not. We're talking about jurisdictions where we have waste management laws, we have systems, we have councils that go out and collect your bin. The vast proportion of the world's populations have none of that. So we need to develop technical systems and the ability to manage materials irrespective of human behaviour. And that's one of my perspectives about changing how we behave with residual plastic. If we can get all the residual plastic as residual plastic, then the system will start to get value out of that, even if the public haven't. Okay, so I think you need system resilience, you need consistency, and you need to keep battering away on the public messaging and the behaviour change and the education. It's really important. But the system has to have the resilience first, because if it doesn't, and you fail with the behaviour change, and we are to some extent failing with that, then we're not going to perform.
Can I just comment? Sorry, can I just comment on that as well? I mean, years and years ago, the government used to issue public information programs. You might remember them. Look right, look left, look right again before you cross the road. Sorry?
Click every trip.
Click every trip. And a lot of them were connected with safe motoring. But, you know, as long as they put out fair, balanced messages, I would say that is a very fertile field for the government to make an advance into. Yeah.
Can I just add? I think that's a really good point. In COVID, we were all encouraged to wear personal protective equipment. The government never mentioned about responsibly disposing of your PPE. What a missed opportunity, and we saw it everywhere, didn't we? Yeah.
But fundamentally, education is the basis for, you know, behavioural change. But that will, clearly, and education is a lifetime. It's going to take a long while to get behavioural change on a. Yeah.
Most of the world.
Yeah. Okay. Anyone who wants to have the last word? Coffee. Yeah. Good. Well, I'd like to thank you as a very tolerant audience coming up with some very challenging questions.
Well, I think we might start, seeing as we're already 5 minutes past the starting point. My name is Richard Lambert. I'm at the National Oceanography Centre in Southampton, and I'm really delighted to be here with such a very good collection of people speaking. I mean, apart from me, of course, but a good a set of invited speakers, should I say. So I'm absolutely delighted by the 4 who have been accepted this invitation, although unfortunately only 2 of them are here in person, which is Alex Billings over here and Katja Papatsava here. So in addition to that, we have Paul Boisseau from Exeter and Alice Hazelhurst from Leeds, and who are going to be presenting remotely, and hopefully, well, Phil tells me that all that is all under control and there will be no little glitches on that front.
Famous last words.
Yes, so the first off, and in contrast to your agenda here, the agenda outside is actually the correct one. And so Paul is going to speak first, followed by Katja. So is Paul online?
Can you hear us, Paul?
Hello, everyone.
Can you hear us, Paul?
Yeah, I can hear you.
Yeah. I think we're ready to go when you are.
Excellent. Okay, very good to see you, Paul. I don't know whether other people have had introductions, but I can say that the crucial part of the work that Paul's going to talk about is his work on tyres, which of course, and all of the speakers are looking at, I'm going to be talking about really quite contrasting aspects of plastic pollution. And one of those which we have enormous uncertainty is on tyres, and Paul is going to tell us something about his work on that. Over to you, Paul.
Okay, thank you very much. I will share my screen. Up. Can you see the presentation?
We could, it's just been dragged off the screen.
Okay, sorry.
Yeah, we can see that.
You can see the presentation? Okay. Good. So, good afternoon, everyone. My name is Paul Boisseau. I am a research fellow at the University of Exeter, and it is a pleasure today to give you this presentation. So let's jump into the presentation, which is called a deep dive into the chronic toxicity of tire particle mixture and their leachates. So first of all, a brief context about tire pollution. There is a high tire tread particle pollution in the environment. We estimate that approximately 1.4 kilogram per year per car are released on the roads. And from that amount, approximately 18% are reaching a freshwater compartment. And on top of that, tire industry is forecast to increase in the coming years. We find high environmental concentration. The low range will be from a few hundred microgram per liter up to about 3 milligram per liter. And the higher range concentration we can find in the environment can reach up to 30 or 50 or 60 milligram per liter. So all this tire pollution will exert long-term pressure to ecosystems with both a physical toxicity. Tire particles are characterized by being elastic macroplastics of irregular shapes, and a chemical toxicity. Tire are characterized by having many additives to impart car safety features, but sometimes it could be at the cost of the environmental safety, because once they are released in the environment, many of these chemicals will be released as well to the environment. So this study was designed to fill the gap about the very scarce chronic ecotoxicological studies we have and knowledge about tire toxicity. The research questions were this one: what are the chronic toxicological values of pristine tire tread particles and their leachates? Second, are life history traits impacted under chronic exposure at environmentally realistic concentrations? And which chemical additives are involved? So the studied species was Daphnia magna, which is a freshwater invertebrate at the base of the food chain. So I have prepared in the lab a mixture of tire particles, which were prepared from 5 different tires of all-season type from a well-known brand. So they were cryo-milled, and a mixture was prepared. And then I've performed 4 chronic experiments of 2 kinds. The first kind was a direct exposure to a mixture of tire particles, first starting from high concentration, and second, which was kind of a repetition, but at lower concentration, which were more environmentally realistic concentration. And the second kind of experiment was exposing animals to leachate. What I call leachate is when incubating the mixture of tire particles in water for a period of time. In this case, it was for 7 days. Well, many of the chemical additives will be released in their surrounding environment. So they are leaching from the particles to their surrounding. And at the end of the incubation time, I filter out all the particles and I expose the animals to the leachate, which are particle-free, but having many additives. And so the each experiment was run for 3 weeks exposure. Particles were characterized in terms of their shape and size distribution. You can see on this graph that the smallest fraction, the smallest size, were the most numerous of particles. And you can see on this scanning electron microscopy the shape of particles, which were of irregular shape, with typical edge, typical of a cryo-grinding technique. This is the first result for the first round of experiments, which correspond to the survival in the experiment with particle mixture and here with leachate. So on the left-hand side, you can see that at the highest exposed concentration, after only a few days, it induced 100% of mortality. And in the case of leachate as well, you can see that at the highest concentration, after only a few days, it induced 100% mortality. So from these different survival curves, I was able to extract the survival at different concentration and to build survival models at different time of exposure. Here at 2 days of exposure and here 21 days. And from these models, I could extract useful toxicological values. For example, the HC50, which is the concentration that induced 50% of mortality in the population, which in the case of tire particles, it was approximately around 50 milligram per liter. And in the case of leachates, it was approximately 500 milligram per liter. So the overall conclusion here is that pristine tire particle mixture were more toxic than their leachate counterparts. These are the survival results for the second round of experiments at lower concentration, which are more environmentally realistic concentration. We can see that the only group for which statistical differences were detected was the group at 50 milligram per liter of tire particles. Interestingly, I have an additional controls with polyethylene microplastics, and no statistical significant effect were detected on this group, which means that tire particles were more toxic than commonly found microplastics of polyethylene. In the case of tire leachate, I didn't detect any statistical significant effect. I observed as well effect on the reproduction of daphnids here for the tire particle experiments. So in this case, I observed first an increase of the reproduction, and after this threshold, a decrease of the reproduction. And this pattern of increase of reproduction was consistent in the second experiment. However, in the case of the leachate experiment, I observed mainly a decrease of the reproduction, and it was as well consistent in the second experiment, a decrease of the reproduction. I observed also a lot of effect on the morphology development of animals, and especially on daphnid tail at 50 milligram per liter in the case of tire particles, and on the body length and body width in the case of tire leachate at 50 and 12 milligram per liter. I observed as well an important uptake of tire particles in the digestive tract of animals. As you can see on these different photographs, the black particles here were ingested in their gut. If we zoom in, you can see more clearly that the particles were ranging from approximately a few micrometer up to about 100 micrometer. And if we zoom in again, you can see that in some cases, particles were very stacked with each other, which means that they may potentially disturb their normal digestive system. And this uptake of particle was dose dependent. Then the leachates were fully characterized in terms of additives. So first with metals. So metals in leachates were quantified, and the predominant metal was the zinc, and then followed by the titanium and the strontium. And then the organic chemicals were characterized in leachate as well with two methods. And the first method was a non-target method. So among all the tires, so it was quantified in each of individual tires, as well as in the mixture. And all these tires shared 54 different chemicals. So 54 different chemicals were quantified that you can see on this heat map. However, most of them were not identified, but several were identified, which are those that are written on the left-hand side of this heat map. And many of them are known to be very toxic. And then a second method, a target method in this case, was employed with a list of probable chemicals that we can find are known to be tire additives and known to be found in the environment and related to tire pollution. And many of them were indeed quantified in these different tires as well as in the mixture. The predominant was benzotiazole, and in second position, the diphenylguanine. Many of them are known to be very toxic. However, as well, many of them did lack sufficient toxicological information. So I tried to find information in the literature, but there was almost no information. So there is a lot of further investigation to do in that sense to better characterize these different chemicals. So in conclusion and overview, we have seen that both pristine tire particle mixture and their associated leachate were able to induce important effects on the survival, the reproduction, and morphology of Daphnia magna, which is an invertebrate at the base of the food chain. We have seen that pristine particles are more toxic than only tire leachates. Many chemicals are insufficiently characterized, especially in terms of their potential toxicity, and that some environmental locations are above chronic safety limits. And if there is one take-home message, I would say that among all the microplastics, tire particles is one class of microplastic of particular concern. Thank you very much for your attention, and maybe if you have any question, I will be happy to answer.
Great, thank you very much, Paul. Lots of people clapping. And what we're planning to do is to have a question session at the end. And I gather from our wonderful Phil, the IT guy, that your image is going to be above the physical speakers. So if you can hang on to the end, Paul, that would be really good. I know I've got a number of questions, and I expect some of the people in the audience have too. So, is that okay with you, Paul? You hang on, and then...
Yeah, that's okay, but I'm sorry, there is an echo with your microphone, so it's a bit difficult for me to understand very well, but I will try to understand what you're saying. Sorry about that, because with the echo, it's a bit difficult.
Okay, thanks for alerting us to that. Alex is probably around somewhere. It's probably because it's going through that speaker and through this one as well, right? Okay. Right, Katsia is next, and Katsia is a colleague of mine at the National Oceanography Centre and has been working on, well, she'll tell you what she's been working on. It's about aquatic environments and the microplastics in those environments. Over to you, Katsia.
Good afternoon, everybody. Thank you very much for introduction, Richard. So this afternoon, I will tell you a little bit about the work that we've been doing in terms of tracing the invisible microplastics in different aquatic environments. So before I proceed with my talk, I would like to acknowledge the effort of everybody in our microplastics team, and Richard in particular, who has been leading the group for about 10 years now. So plastics are found everywhere in the ocean. Recent studies estimate that it's about 3.5 million tons of plastic float in the surface ocean alone. And every year, pretty much the same amount is being added to the ocean environment. So thinking about these numbers, you might imagine that the ocean looks like this, full of floating large plastic litter, which we term microplastics. But in fact, most of the ocean is still pretty blue. And turns out that plastics, they neither float in the same, most of the plastics neither float in the surface nor very well visible. And this is because when in the environment, large plastic pieces break down into much smaller plastic particles called microplastics. So I'm giving you the size range right at the bottom. Where's the laser? And we demonstrated this with our basin scale measurements in the Atlantic Ocean. And we published this study back in 2020, where we showed that most of the plastic pollution is actually hiding underneath the ocean surface, and this pollution is actually in a very small size range. We only looked at the top 300 meters across this track in the Atlantic Ocean, and we looked at concentrations of 3 most wasted polymers: polyethylene, polypropylene, and polystyrene. And what we have found that the mass of these 3 polymers in top 300 meters already exceeds the amount that we thought we have put in since 1950s. So this is quite a staggering discovery, and what we have shown is basically it was a tip of the iceberg. And we highlighted that there is a critical need for robust assessment of the sources of plastics in the ocean, their loads, their pathways, their fate, so that we can assess their impacts reliably. Plastics are contaminants, which means that they're not supposed to be in the environment in the first place. And because they're so diverse and versatile, they can pose a variety of risks and a variety of hazards. And the diagram over here gives you a broad spectrum of potential risks that plastic pollution could have in the marine environment, or rather in the aquatic environment. It starts from just causing a distress to people when they see plastic litter on the beaches. Plastic as a particulate contaminant can pose physical damage and cause entanglement and strangulation, oxidative stress to marine life. Plastics are also chemically very, very complex. So some of the additives and plasticizers that are added into plastics are toxic, bioaccumulative, and persistent. So, and because they are ingested by marine organisms at the very base of the food chain, they can go up the trophic level and ultimately reach the human diet. So it is very important to understand, to answer the questions about these potential risks and how long it takes for these risks to occur, whether it's a short term or whether they are long term. So at NOC, we have been addressing the very fundamental questions about plastic pollution, focusing on exposure to this contaminant, because that is an essential component of this risk equation. So what we mean by exposure is answering the questions of how much plastic is out there, what is it made of, what the sizes of those plastics are, where do they come from, where do they end up, how long they stay in the environment, and what is their fate. So the questions of exposure and persistence of plastic in the marine environment is what defines research that we do at National Oceanography Center with respect to this issue. And in the next few slides, I will tell you a little bit more about the projects that we're currently working on. So this figure summarizes the NOC microplastics research in space and size. So we work in the variety of environment. We're not only working in the ocean, we also do our research in the terrestrial environment, in fresh waters. We look at the coastal waters as well. And lastly, we will look at the plastic abundance and distribution in the surface ocean and in the deep sea as well. We'll look across different sizes of plastic particulate contaminants, from very large ones down to about 10 microns in size. But mostly our research is focused on microplastics. So we look at the transport of plastic into the ocean, and one of the projects that we're currently working on looks at, it's called LabPlas, and it looks at the input of microplastics from two major European rivers, River Elbe in Germany and River Thames in the UK, and how much plastic they carry into the North Sea. So what we're trying to understand in LabPlas is what the sources of plastics are, how they're transported, how they're distributed across different pathways, and what impacts they will be having on biota within those environmental compartments. So here's an example of us having fun collecting plastic samples on the River Thames. We collect water samples in the surface water of the Thames at depth, and we also bring the sediments back. And this is an ongoing project. So there's lots of work in progress, but we are already getting some quite exciting results, which you can see on the figure to the right. So these are the plots of abundance of plastics in River Thames and River Elbe and in the North Sea. So we can see the different concentrations of these contaminants in winter and in the summer. And you can also see the polymer composition of the microplastic loads in those environments. And interestingly enough, in all sites, it's predominantly polypropylene. It is also very critical to robustly adjust the concentrations of plastics in the ocean. Largely because most of the ocean still remains undersampled in terms of microplastics, especially the ones in a very small size category. And here's an example of our collaborative work with the citizen scientists. So in 2023, we collaborated with the global yacht race, the ocean race. So the sailors were given pumps, and as they sailed across the global ocean, as they raced, they also collected microplastic samples for us, which were analyzed in the lab. And as a result of this joint effort, we came up with a sort of updated version of surface plastic concentrations in the global ocean. And interestingly, what this plot shows is that we see accumulations of plastics not only in the places where we usually expect them, like in the coastal waters, for example, or in the middles of the oligotrophic gyres. We also see a lot of plastics in very, very remote part of the planet, like in the Southern Ocean, for example. And the concentrations are comparable to the coastal regions as well. And we also determined the polymer composition of these plastic loads. And again, it's the usual suspects that crop up. Polyethylene was the most dominant one, followed by polyester, polystyrene, and polypropylene. As I mentioned earlier, persistence of plastic in the marine environment or in the aquatic environment is still a very important question, and this question remains largely unanswered as well. So what happens to the plastic once it's in the environment? We know that it ends up at the seabed ultimately, but how long does it actually take for the plastic to sink to the bottom of the ocean, and how the sedimentation varies with respect to polymer composition and how it varies in time and space. So at NOC, we're very uniquely positioned to answer this question, and we do it by directly measuring what actually sinks down to the abyssal depth in the ocean. So we use these devices called sediment traps. They are, in essence, rain rain gauges, which we deploy in the deep ocean, and they collect everything that is particulate and is sinking down to that depth, including microplastics. So advantage of these instruments is that they sit in the ocean for about a year or so, and throughout this year they come back with a continuous series of something that we call particle flux. So from that particle flux we can also determine the flux of microplastics. And another advantage is that we can also study the controls over the sedimentation of plastics to the deep sea by looking at the links with the ocean biogeochemistry and specifically at the interactions of plastics with natural particulate matter like aggregated phytoplankton detritus and fecal matter from zooplankton. So, as a part of another European project called Atlantico, we have these sediment traps deployed at 3 locations in the Atlantic Ocean. And these sediment traps have been sort of repurposed to look also at plastic pollution. Historically, they've been looking at the amount of carbon that the ocean draws from the atmosphere and transports it, sequesters it in the deep sea. So we have the time series of these particle flux observations running from 1989 at the Porcupine Abyssal Plain, so that's the very top side map, and at Nog and Sog in the centers of North and South Atlantic oligotrophic gyres where plastic tends to accumulate. So these sites are also very distinct in terms of their biogeochemistry and productivity. So it's very interesting to look at how these factors affect the microplastics flux at those sites. So it's also work in progress. So here's an example of what we have measured so far at these 3 locations in the year 2010. And as you can see, there is a huge variability in terms of what we see in terms of magnitude of the flux of polymer-specific plastics, and also different types of plastics that end up at these 3 locations. But again, we can pin down the usual suspects that are present in all 3 sites, like polyethylene, propylene, and polystyrene. To date, we analyzed all the samples, and just to give you an idea what the results are looking like, so we identified 129 polymer types, so those are thermoplastics, thermosets, elastomers, and paints. And we also identified 69 different types of additives, plasticizers, and adhesives. So this is a work in progress, and in about half a year or so, we will have a lot more to show, so watch the space. And if you have any questions, feel free to ask. But I guess that will come later on.
Great, thank you very much, Katja. And keeping to time, both of the speakers, really good. And so thank you very much. And now, Alex, your time. And Alex is an environmental organic chemist, and so brings a particular perspective, not only on, I notice, on the pesticides in honey, but also on additives, which is obviously a key focus of this whole meeting. So over to you, and thank you.
Thank you, Richard. So I'm Alex Billings. I'm an environmental chemist at the UK Centre for Ecology and Hydrology. And today I'd like to give you an overview of plasticizers in aquatic environments, followed by a bit of a case study of some work that we've been doing. So just so we're all on the same page, plasticizers are additives, so these are chemical compounds added to plastics to increase their flexibility. And they're primarily used in PVC applications for a wide variety of reasons. And they're one of the most widely used plastic additive globally. For example, 1.5 million tons are produced in Europe annually. So over the last 15 years or so, there has been a kind of a shift in the plasticizer market. So historically, a group of compounds known as phthalates have been the most widely used. and we detect these widely in the environment and in biota. But recent restrictions in the EU on some plasticizer, on some phthalate compounds, have resulted in the kind of general phasing out of some of these over the past 15 years. So in 2005, they accounted for about 90% of European plasticizer market, but now it's, in 2020 it was down to about 50%. And this has driven a diversification in the market. So there's been an increase in the use of so-called emerging plasticizers. So these are non-phthalate alternatives to these restricted compounds. And these have increased in use over the last couple of decades. But whilst we know a fair bit about phthalates in the environment, the occurrence of these emerging plasticizers and their effects are not really widely known. So why do we find plasticizers in the environment? Well, the vast majority of them are not actually chemically bound to the polymer matrix. So they can be released from the polymer over time. And it's quite a complex process, so the rates and the extent to which this happens are influenced by things such as the type of polymer, so whether it's polypropylene or polyethylene, and the actual kind of chemical composition of that, the properties of the plasticizer itself, and also the nature and properties of the matrix into which the release is happening. So, for example, we might expect the release of plasticizers to occur more readily in organic-rich matrix such as sediment, as opposed to something like sea or salt water. So, aside from the kind of in situ release of plasticizers from plastic contamination in an environment, there are other potentially direct sources of plasticizers themselves into aquatic environments, and I've just kind of listed 4 here on this slide. So obviously, given that the majority of them are used in urban and industrial settings, this can act as one source. Furthermore, waste disposal sites, so landfill sites, we know that phthalates are widely present in these, and some studies have indicated that there may be potential for downwards and lateral transport, so entry into groundwater or surface water from these sites. And this may be particularly something that we need to look into in the future if we're going to be tackling the effects of climate change, so increased flooding and erosion, particularly of legacy landfills, which may not be properly lined, literally just a hole in the ground. You know, back in the 50s and 60s, the kind of legislation wasn't quite there. So, you know, this is something that we need to focus on in the future. And additionally, wastewater treatment. So whilst the majority of plasticizers are retained in the sewage sludge, particularly the lower molecular weight plasticizers, we know they are released into rivers in the effluent. And then this sewage sludge, over 90% of the sewage sludge that we reduce in the UK is spread on agricultural land. There's a soil amendment, which is very important for soil health, but it does contain these plasticizers, which then potentially could be washed into watercourses. And also, there's quite a good body of evidence that, linking plastic mulch use in agriculture to the presence of plasticizers in soils. So, why do we care if plasticizers are in the environment? Well, studies have shown that the majority of phthalates, half-lives are typically on the scale of days to weeks. But in certain conditions, they can be very long-lived. For example, in sediments, the half-life, so this is the time it takes for the concentration of a substance to halve, can be up to a year. And we've detected phthalates in particular in multiple different aquatic species, and their exposure of phthalates to aquatic species has been linked to, for example, alterations in metabolism and reproduction. However, linking these kind of lab exposures to actual effects on wild populations of chronic plasticizer exposure is tricky. And we also don't really, most of this is based on information about phthalates, so we don't really know the fate and effects of these emerging plasticizers, so their replacements. So just to finish off, I'd just like to share a few slides of a case study of some work that we've been doing in the Forth Estuary up near Edinburgh, where we were looking at the levels of phthalate and emerging plasticizers in the sediments. So the Forth Estuary is relatively urbanized. The details of this map aren't really that important, but just kind of shows some of the key potential sources of plasticizers. So we've got a number of legacy and operational landfill sites within the catchment. multiple wastewater treatment outfalls directly into the estuary, which may come from municipal or industrial sources. And it's also home to kind of internationally important seabird colonies. For example, centred around the islands of Inchkeith and the Isle of May, we've got some pretty important colonies of particularly northern gannets and shags. So what did we do? We went and, I say we, I didn't do the sampling myself. We went and visited 50 sites, collected a number of bed sediment samples. It was designed to have two study areas, so what we call the inner estuary and the outer estuary. And we collected them in a range of seasons, so this is from November 2020 to July 2021, because you can get very, very large changes in channel flow between different seasons. They were collected at a range of depths in the water column. And then we extracted the plasticizers from them in the lab and measured the amounts of 8 phthalate and 3 emerging plasticizers in the sediments. So this map here shows so this is the sum plasticizer levels. So this is all those plasticizer, the concentration of them added all together in winter in the estuary. So we can see that they're clearly higher, they're significantly higher in the inner estuary. So 80% of the most contaminated sites were located closer towards Edinburgh. This is probably is not surprising given the proximity to sources, but it also indicates potentially the transition from freshwater to saline water. So at this boundary, at the head of the estuary, we might expect salting out, so the deposition of suspended sediments in the river. Once that kind of transition to saline water occurs, they'll just settle out into the bed sediments when they may themselves be carrying plasticizers, say from wastewater treatment plants or agricultural land further upstream. And the graph on the right shows how the amount of plasticizer kind of change with water column depth. So generally, the most contaminated sites were the shallower sediments, which again relates to proximity to the coast, proximity to sources. Just touching on the actual kind of profile of the plasticizers that we found. So the most abundant and most frequently detected was this DEHP, which is a phthalate plasticizer, the most commonly used globally. So it's not surprising that we find it in the highest concentrations. Don't know what's happened there. We also found this plasticizer, DEHTP, so this is a terephthalate plasticizer. This is one of the emerging plasticizers. It's actually the most commonly used emerging plasticizer. Whilst it was in relatively low concentrations, it was detected pretty frequently. So, for example, in over 50% of the samples in winter, we detected this plasticizer. So the kind of take-home message from this is that whilst phthalates remain the dominant plasticizer in terms of the profiles in the environment, at least in this case, emerging plasticizers are as frequently distributed, but at relatively low concentrations. So I'd just like to leave you with kind of 3 knowledge gaps for potential future plasticizer research. So we really need to get a handle on how the occurrence of these emerging plasticizers compares to phthalates, and what might the temporal and spatial trends be as the market continues to diversify. How does the fate of these emerging plasticizers compare to phthalates? So, for example, what are the degradation rates in the environment? Do they partition differently to different environmental media than the phthalates do? And also, we kind of need more research into the uptake and effects of all plasticizers, be that phthalates or emerging plasticizers in aquatic organisms. So these might be the rate at which they're eliminated from the body, the potential for accumulation or transfer up the food chain, and also the effects thresholds in wild populations. That's me.
Great, thanks very much, Alex. Lots of really interesting information there, really good. Now, Alice, hopefully you are around. So Alice is going to be talking about, she's got a lot of expertise in the textile industry, and particularly on the effects of washing on textiles and the microfibers that originate from that. And I guess that's what she's going to be talking about now, yarn characteristics and the knitting process, influence of microfiber release in laundering. Are you there, Alice?
Yes, hi, hope you can all hear me.
We can, loud and clear. Over to you.
Brilliant. Thank you. Hi, I'm Alice. I'm a research technician for textiles in the School of Design at University of Leeds. Yes, my area of research is textiles and specifically microfiber pollution from textiles. I'm going to present some of the research that I've conducted recently with my colleagues, Mark Sumner and Mark Taylor, which has investigated the influence of yarn characteristics and the knitting process on the quantity of fibre release in laundering.
Alice, do you think you could go on?
So I will provide a brief introduction to the topic of microfibres in laundering and discuss some of the existing knowledge from the literature relating to the influence of different textile characteristics. I will also talk a little bit about fibre damage and fibre release during the textile manufacturing process. And then I will go on to discuss our recent research, so the methods that we've used and our findings for some different yarn characteristics.
Alice, do you think you could go on to presentation mode? You're in whatever the other mode is.
Sorry about that. Let me see. Oh.
Alex knows apparently you need to go into display settings at the top, second from the left. Up a bit. There.
Yes.
Yep, you got it. Great, thanks, Alice.
All good now? Sorry about that. Okay, so microfibers in this context, we're talking about small fragments of textile fibers that can be detached from fabrics and released during the laundering process. And then they obviously have the potential to end up in the aquatic environment if there isn't adequate wastewater treatment in place to retain them. So this fiber fragmentation and release can occur from fibers of all compositions. Synthetic fibers, such as polyester, especially because that's heavily used in the textile industry and in clothing. This has received a lot more attention from researchers and from the media and so on, because it falls under the umbrella of microplastics. But there is also a lot of evidence of microfiber release from natural origin fiber compositions, and particularly cellulose-based fibers, which again are used regularly in textiles. And these are being found typically to be much more abundant in environmental samples than the synthetic fibers. There's been some assumption that these being natural origin would lessen their environmental impact. But if they're coming from textile products such as clothing, etc., they have experienced a lot of human intervention. So they will have been through intensive processing, potentially have dyes, other chemical finishes applied to them, as well as other things such as detergents and softeners that might be interacting with them in the consumer use phase. So all of this can affect the potential risks of these fibers once they reach the environment. And there's an increasing body of evidence suggesting that these cellulose fibers are not biodegrading readily in aquatic environments. And it is also important to acknowledge that while laundering is a significant pathway for textile fibers to the environment, these microfibers can be generated at any and all stages of the textile's life cycle. So not just in the washing process, but in general use and wear, as well as in the processing stages and at end of life as well, depending on how disposal is managed. And through all these different stages and different mechanisms that fibre can be released, they can reach the environment by other pathways, such as atmospheric deposition and soil transport as well. But I will focus on laundering here for this session on the aquatic environment, and laundering is the method that we've predominantly used to collect and quantify microfibre release throughout our research. So a lot of the earlier research in this area looked at the influence of different laundering conditions, so things like the temperature and duration of the wash, but there's been a sort of increasing understanding that it's not just the washing process that's generating these fibres, and so focus is now slowly moving towards the textiles, so looking at the fabric characteristics. And because textiles are very varied and complex, there's not a lot of super conclusive findings that you can point to in the literature at this stage, but there are some more consistent findings, some trends kind of emerging there. So for example, greater fibre release is generally being reported from cellulose fabrics compared to synthetics. This is likely due to a combination of cellulose fibres being comparatively less durable and therefore more prone to damage, and also generally having shorter fibre lengths, which produces fabrics which have more surface hairiness, so more fibre ends protruding from the fabric surface. Similarly, yarns spun from short staple length fibres are tending to release more microfibres than those spun from continuous length filaments, because the shorter fibres have generally better mobility within the yarn structure, and again, you have more likelihood of fibre end protrusions, which could be vulnerable to damage. And there's also been some reports that higher yarn twist can help to reduce microfibre release, because this helps to provide better cohesion and interfibre friction in that yarn structure. And in terms of fabric structure, the tightness or the density of the fibre structure seems to be the most important factor there, with tighter structures releasing fewer fibres than looser, more open constructions. Again, because that tightness is really helping to reduce fibre mobility and improve the cohesion of fibres within the fibre assembly. And whilst this research into the mechanisms of microfibre formation and release is still emerging, this is actually kind of a long-standing issue within textile manufacturing settings. So in this context, it's usually referred to as fibre fly, but it is essentially the same thing. It's small fragments of fibre that are detached from the fabrics, from the yarns during various processing stages. And these fibre fragments can become hazardous in these working environments. For example, if they deposit in large quantities on machines, they can cause faults, they can potentially present fire risk, and they're also dangerous if they're inhaled by workers. There is a specific respiratory disease caused by inhalation of cotton dust, which gets called cotton lung disease. So this isn't a new issue. And so for these reasons, there are often already practices in place within textile manufacturing settings to remove these fibres through extraction and ventilation to improve the overall working environment and the safety and efficiency in those places. And then there also has been a lot of research into the mechanisms of fibre fly, how that's being generated and what factors are influencing it. And as you might expect, these findings are very similar to what we're seeing now with the microfibre research. So yarn hairiness, yarn twist, and fabric tightness being important factors. And it's also worth noting that although a lot of these, this fibre fly is managed and extracted from the working environment, these fibre fragments can remain in the manufactured fabrics. And this is part of the reason why we see generally the most microfibre release in that first domestic wash once the fabric reaches the consumer. So for our research, we wanted to look more closely at some different yarn characteristics, namely the yarn linear density, the yarn spinning system, and we also looked at 2 different fiber compositions. So we sourced staple polyester and cotton yarns for this work from the same manufacturer, so that we were reducing that as a variable, and they're also undyed and unfinished. So again, just cutting down on variables there. We just wanted to compare 2 different linear densities, so 30 tex and 15 tex, and 2 different spinning systems. So we have a vortex spinning and conventional ring spinning. And to also investigate the influence of the knitting process itself, we compared microfiber release from just the loose yarn hanks with the same mass of yarn then knitted into a fabric swatch. So we used a simulated laundering process to wash each of these samples, followed by vacuum filtration of the wash liquor to collect the microfibers so that we could quantify them. And here are some of the results then. So comparing the yarn hanks with the knitted fabrics, first of all, for the polyester yarns, there was generally more fiber release from the yarns in the loose hank form, whereas for the cotton, it was the opposite, and there was generally more fiber release from the knitted swatches, so after the yarns had gone through that knitting process. So that's demonstrating to us that the cotton is experiencing more fiber damage from that knitting process. I have included a fairly simplistic diagram of the yarn path for creating the hanks from a yarn rack reel and for creating the knitted samples on a knitting machine. And the main thing to take away from this is that in the knitting process, there's a lot more points of contact between the yarn and the machine, and there's also a lot more yarn-to-yarn abrasion as the rows of the knitted fabric are formed. So there's just a lot more opportunities for fiber strain and fiber damage to occur. But it's interesting to see that that didn't have a significant effect on the polyester yarns that we tested, but it did on the cotton. And then looking more closely at the different yarn characteristics. So these results are all from washing of the knitted samples. So we found that the spinning system did have a significant influence, with the ring spun yarns generally releasing a greater quantity than the vortex spun yarns. And this was in line with our expectations because vortex spinning is known to produce smoother yarn with better fiber alignment and reduced hairiness. And you can see that in the images here as well. So image A is one of the ring spun yarns, and image B is the corresponding vortex spun yarn. And hopefully you can see there that in the yarn and the knitted form, there's a lot less fiber hairiness and fuzziness in that sample B. And for the yarn linear density, to make sure we had a fair comparison here, when we knitted them, the finer yarns we knitted double-ended. So this meant that the same mass of yarn was in each of the samples, and overall the fabric stitch density would remain the same as well. So we didn't further twist the yarn ends together. So you can see in this example, image B is one of the 15 tex yarns. So you can see that there are 2 ends of yarn in each of the knitted loops, compared with image A of the 30 tex yarn where only 1 end is used. So our results actually showed that there were no significant differences between the fiber released from different yarn linear densities when tested in this way. But it's interesting to note that if the yarns were differently twisted or plated through that knitting process, that might not be the case. And lastly, comparing the different fiber compositions, we found that the cotton yarns always significantly released significantly greater quantities of microfibers compared to the corresponding polyester yarns. Again, somewhat in line with expectations, because polyester is generally characterized by better strength and durability than cotton. And you can also see from the images here quite clearly, I think, that in image A, there's a lot more fiber protrusions and a lot longer fiber protrusions as well. So image A is the cotton sample. And then in image B, this is the polyester sample. So even though these polyester yarns are made with staple length fibers, so those filaments have been cut short, they're not continuous length. In the way that the polyester fibers spin up is a lot smoother, a lot less hairy. So in the cotton yarns, much more potential for fiber damage and detachment in the way that we've tested them here. So briefly to summarize, we found that fiber and yarn selection is important if we want to reduce microfiber release from textiles, and cotton yarns typically release more fiber than equivalent polyester yarns, and vortex spun yarns typically released less than equivalent ring spun yarns. And we also pointed to the importance of fiber damage within the manufacturing process. However, the extent of that damage seems to be dependent on the fiber composition for the samples tested here. Thank you very much for your time.
Great, many thanks, Alice. That's great. Now we'll see whether we can get our two speakers up on the bench and with pictures behind of Paul and Alice. We'll see, and that's certainly covered an enormous range of topics, and certainly from my point of view, there's really an enormous number of very interesting questions raised during these presentations. So I hope you, and I don't know whether the people online can ask questions, but certainly you guys here physically present will have some questions for the four speakers, I suspect. Yes? Are we in business? Almost.
Just working on it, but carry on by all means.
Right. Okay, so I don't know quite how this is going to work, but we'll... Yay! We've got both Paul and Alice. Right. Paul, am I echoing terribly still? So bad that, in fact, Paul can't tell that I'm speaking to him clearly. Never mind. Paul, can you hear what's going on here?
Yes, I can hear, but there is an echo, so I will try to understand what you're saying.
Okay.
Yeah.
So let's hope. Right. Question over there.
Yeah. Let's echo on that one.
Oh, okay. Right. Good.
Thank you very much indeed. My first question is actually for
Would you like to just introduce yourself?
Yeah,
to say
sure. I'm Mike
who you are?
Boswell from Plastitribution. And my first question is for Katsia, actually. I'm a fairly simple physicist, but the density of seawater is about 1.03. And yet we have plastics with densities for polyethylene and polypropylene and polystyrene below 1. And other materials like PET and PVC above 1.03. I'm just wondering about the influence of that. To me, that's a sink float equation, but perhaps I'm just too basic in my physics.
Thank you for your question. It's actually a very important one. So knowing how plastics sink down to the bottom of the sea is very crucial to understand, because obviously physically they won't be sinking on their own unless their density is greater than that of the seawater. So what happens in the natural environment is plastics interact with other particulates. So I mentioned phytoplankton, detritus, aggregates, which also aggregate with microplastics. And as they sink down, they carry plastics down to the seabed. So that's one mechanism. Another one is the moment plastics are in the environment, they become a matrix for biology to grow on. So the moment the biofilms appear on plastics, the density changes as well. So to the point that ultimately it becomes larger than that of seawater, it starts sinking. Physical processes in the ocean also will affect the downward flux of microplastics. So things like downwelling, when the parcels of water literally move down the ocean. Another aspect is microplastics are being eaten by marine biota. So as fecal pellet or marine poop, so to say, is produced, it will contain microplastics as well. So that's yet another way for plastics to get down as a part of fecal pellets from either zooplankton or fish or organisms higher up in the food chain.
Thank you. That solved a mystery for me. I've got a question for Alex now, which was in your excellent presentation. You spoke about evidence of plastics mulch being a source of plasticizers. Yet my knowledge from the industry is plastics mulch is primarily polyethylene based without plasticizers. So just slightly curious about that one. I'm not really aware of plasticized based materials being used in that application.
Yeah, so the majority of those studies were conducted in China, where I think regulations may be different to here. I don't know of any studies, any field studies in the UK that have looked at that specifically, but certainly in other parts of the world, that could be a potential source, but possibly not in Western Europe as much.
Yeah, I think that may be the case. My final one's for Alice, actually. I mean, I think being in the plastics industry, we feel like we are the major culprit of microplastics in the environment. And yet it's only sort of recently that I think textiles has come to the fore in terms of the very nature of what you presented in terms of abrasion in use, wear and tear, abrasion in washing that's caused the problem. So I'm going to be controversial, ask a question. Do you think microplastics in the environment are a more significant cause of that concentration is coming from fibres or from what we would call traditional plastics applications?
Yeah, it's hard to say really. I mean, there are reports that I think like 35% of microplastics are coming from fibres or fibrous, so from the textile industry. I think personally, maybe this is controversial to say, coming from the textile side of things, that actually disposal of, if you like, macro scale textiles, so just disposal of garments in general, is more of an issue than the microplastics side of things. We dispose of a lot more textile waste in general than we're seeing the mass of plastics, microscale plastics coming out the other side. So I think for sure it's a big contributor, but I don't personally think there's enough evidence to say that it's the biggest contributor at this stage.
Right. Any more questions from the floor here? I've got a few questions, but it'd be good to hear from other people if they have some. No? Okay. Well, so there were a number of points that I was very particularly interested in, and one of them was from Paul, who was doing these very nice LC50 measurements, and I missed, and maybe it was just my own lack of attention, but I missed whether the concentrations being used were ones which were similar to those in the environment. So that's the first part of the question. And the second is whether there are approaches which he's got in mind for looking at prolonged sublethal exposure at much lower concentrations, which certainly for us in the oceanographic community, the concentrations are very low, but they are, of course, present for very long periods of time, for multiple generations. And it strikes me that someone such as you, Paul, you've got sort of experience of doing these sort of calculations. And how do we move forward for looking at prolonged sublethal exposure, which are possibly going to be of enormous importance in the future? So it's a sort of two-phased question really for you.
Thank you for this question. So for the first question was where the concentration environmentally realistic, if I have understood your question.
Yes.
So I did two sets of experiments. The first set of experiments I started at very high concentration, which were not environmentally realistic, but going downwards. So the last few concentrations were environmentally realistic. And the second round of experiments, they were environmentally realistic. Even if, so I started from 50 milligram per liter, going down to 3 milligram per liter. So they are environmentally realistic, but still it corresponds to quite high concentration for the environment. So yeah, the thing is, in the environment, we may find many diverse concentrations. So to answer for the second question, very long-term exposure. I mean, in ecotox, it's always better to expose at for an extended period of time to really capture what it could have as effect. So this exposure were for 3 weeks. They are considered chronic, but of course we can still extend the exposure and at lower concentration that would reflect a bit what is most often encountered in the environment. So, but at the moment, so even if there are some studies about that, about quantification of tire contamination in aquatic system, to have a complete understanding of what's the concentration distribution in the environment, to know if, for example, okay, if 3 milligram per liter, is it something that we only find sometimes, or is it very common? The same for 50 milligram per liter. Is it, what's the most common? Is it a few hundred microgram per liter? But in any case, as long as these concentrations are rich, with our study, we have shown that they have the ability to induce important biological effects on this animal. And so to implement long-term studies, yeah, it is possible to run, for example, multi-generational studies on these animals. Then if we want to go even closer to a realistic condition, we may consider to have exposure in mesocosm system, outdoor mesocosm system, large-scale outdoor mesocosm systems with, how to say, with some contamination that are not constant, so with some peak of concentration that might mimic what may happen in the environment with weathering effect, with rain and such kind of thing. So yeah, the next step could be to go even closer to what is what we can call realistic, or even more closely realistic. But 3 weeks exposure is already, I think, giving us a quite good understanding of their potential toxicity. Yeah.
Right, thanks, Paul. I was actually wondering whether you were going to talk perhaps about some of the other approaches, perhaps with gene expression or some of those sort of approaches which might be more easy to achieve, or at least they might be more easy to look at over a broad range of types of organism. I mean, I think mesocosms, so it's interesting you're talking about mesocosms. I've got some experience of working on mesocosms, and I'm a bit cautious. I would always be very cautious, in fact, using them because of the enormous variation you get between them. The statistics are usually absolutely appalling, even in doing quite simple things. But anyway, I was just wondering if you had sort of other approaches apart from the more traditional ones, which you very nicely described. But perhaps there aren't any. I don't know. I think we need some.
Yeah, so I do think mesocosm are a very great approaches. But so you were speaking about gen and potential effect on genomics in general. I would say I think they are definitely very good approaches. However, it depends. I mean, in terms of severity of effect, we will have to work at much lower concentration, because I've seen that at even at 12 milligram, 12 and 3 milligram per liter, they had effect on reproduction. So if there are effects at this kind of life history traits, I see less relevant to go for the molecular effect analysis. However, at lower concentration where we don't see any effect neither on survival or growth or reproduction, I would say then, yes, the molecular approaches, especially transcriptomic and proteomics, will give us, I think, very good insight of early biological effects.
Great. Thanks very much, Paul. Right, any more questions from here? Or, I don't know, can people online ask questions, Phil? If they, yes, I wasn't proposing people would be compelled to ask, but perhaps there aren't any online. So I've got one more quick question, unless there are any more from the floor here, and that's for Alice. You didn't mention traps, which have been in the washing process. Various designs of trap have been marketed, and I was just wondering whether you were optimistic that this was a good way forward, and and are there good developments in the types of trap to prevent some of the products of washing going into the environment?
Yeah, thank you for that question. Yeah, it's interesting. I mean, there's been some studies looking at the efficacy of the different types of traps and filters that there are for in wash, and they sort of have varying levels of efficacy, as you would expect. I think from what I've seen, the filters that are fitted to the washing machines themselves tend to be more effective than things like there's some washing bags and like plastic balls and things like that that go in with the washing. Those tend to be less effective, but in all those cases you're still putting the onus on the consumer then to deal with the fiber that's released. So even though it's captured by these filters, you still need to dispose of it somehow. So, you know, if you have a consumer that's not necessarily very responsible and they just rinse the filter down the sink, then it's completely negated any positive effect you might have had. And even if you're just putting them in the bin, you know, still where does that end up? So I think that they're definitely good developments and it's better than nothing, but I don't think it's the be all and end all solution.
All right, thanks very much, Alice. Right, well, it would look as though we've probably, with a number of people escaping already, we've come to the end of this. So thank you very much for your attention and your presence here. And thank you very much to the speakers, Paul, Alex, Katja, and Alice. I certainly learned a lot. I thought there were a lot of this diversity, a lot of very interesting information came out of that. So I'd like to bring this session to a close, and thank you very much, and travel safe.